Close your eyes and settle your breathing. It's easy to picture a few famous moments, big impacts, long winters, but Earth's story also turned on quieter, unseen mega events. Slow pulses that redirected oceans, softened the air, and nudged life onto new paths. Where in the world are you watching from? Share your location in the comments. It's soothing to imagine our sleepy map glowing across the planet. Tonight, we'll drift through the hidden switches of deep time, the gentle forces so vast you can feel them, even with your eyes closed. Imagine the planet breathing so slowly that a single inhale takes hundreds of millions of years. Continents drift together from scattered islands to a single vast land, then loosen and wander apart again. And each motion changes shorelines, winds, and the paths living things can take. At first, the pieces move almost imperceptibly, cratons nudged by convection in the mantle, ocean floors spreading along warm ridges where basalt rises and cools, plates sliding past with a faint grinding that the rock records as slickened sides and fault gouge. Where plates meet head-on, mountains rise like long, quiet wrinkles. Where they pull apart, rifts open as linear valleys floored by new basalt and lakes that glitter in sequence. Over deep time, these motions play out as a cycle. Small continents collide into supercontinents. Supercontinents break, and oceans open and close in a rhythm geologists sometimes call the Wilson cycle, a slow choreography that rearranges the planet's climate controls without drama, and yet with profound effect. When land gathers, coastlines shorten, and the interior of the supercontinent stretches into vast distances from the sea, where summers can grow hot and winters cold because water's moderating hand is far away. Monsoons swell on the flanks where warm land draws in moist air from wide oceans, and deserts bloom in the lee of mountain belts that catch rain and wring it out before it can cross. Ocean currents reorganize because the shapes of basins dictate where water can flow, and the deep conveyor belts that mix heat and nutrients shift their routes accordingly, sometimes feeding upwelling along new margins, sometimes starving shelves that once teemed. Rivers adjust to new gradients and sediment loads, carrying the sand and silt of rising ranges across long plains to the sea, building deltas where the coastline allows and carving canyons when the land lifts faster than the water can keep pace. Life feels these changes as a gentle but firm hand on habitat. Corridors open where shorelines lengthen. Barriers rise where deserts span the middle of the land. Shallow seas flood when the crust warms and bows, then drain when plates thicken and cool, leaving behind blankets of carbonate and evaporite that speak of warm, restricted waters under bright skies. Rodinia gathers in the deep past, a quiet amalgam of earlier collisions that stitched Archean and Proterozoic pieces into a broad continent bounded by long sutures where ancient oceans had once closed. Its interior likely hosted extreme seasonality and deserts punctuated by lakes, while along its edges, passive margins built thick piles of carbonate where warm, clear waters lapped at low-relief shelves. Over tens of millions of years, heat pooled beneath this lid of linked plates. Plumes swelled like slow balloons in the mantle, and the crust began to dome and crack. Rifts seeded by that rising heat lengthened into valleys, then into linear seas as the first threads of new oceanic crust intruded and spread. Continents once touching slid apart, the broken edges trailing strings of microcontinents and volcanic islands as they drifted. The opening oceans breathed salt and heat differently than those they replaced, and winds found new lanes. Life followed, colonizing fresh shores and lagoons with forms tuned to the chemistries and temperatures that the new circulation patterns allowed. Later, Gondwana assembled much of the southern land into a sweeping mass that would spend long intervals drifting across latitudes, carrying forests and deserts alike over the poles and back toward the equator on a leash of plate motion. Collision after collision added terrains along its margins. Arcs of volcanoes guttered where ocean floor dove beneath the edge. Mountain chains rose in sutures where buoyant continents met and locked. At the same time, smaller continents and island arcs wandered in the northern hemisphere, gathering into Laurasia and later drawing near again. As the pieces closed the remaining oceans between them, subduction zones consumed old seafloor, pulling plates like conveyor belts, and the geometry of the globe approached another single land. When Pangaea finally took shape, it stretched almost from pole to pole, a giant with a spine of mountains along the line where its halves had met, and around it a global ocean, Panthalassa, circulated with few obstructions, while a smaller, enclosed sea, the Tethys, nested along its eastern margin like a warm, shallow book pressed between covers. The climate response to Pangaea's mass was patient and complex. In its heartland, far from maritime softness, large deserts spread. Along its coasts, monsoons drew moisture off warm seas and poured seasonal rains inland. On its western margins, facing the broad Panthalassa, storm tracks curved in and out, with the yearly cycle and with the slow wander of the continent across latitudes. Mountain building from the continental collisions made new highlands whose weathering drew carbon dioxide out of the air grain by grain. Rivers carried the dissolved products to the ocean, where they formed carbonates that locked carbon into rock, tweaking the planet's thermostat toward cooler states on million-year scales. Meanwhile, the arrangement of land and sea controlled how deep waters formed and spread. In some intervals, restricted basins stagnated and grew low in oxygen, favoring black shales and quieting seafloor life, while in others, gateways allowed a more vigorous exchange that kept deep waters fresher and shelves busier with oxygen and food. Each of these shifts unfolded gently compared to human time, but their sum traced long arcs in temperature, rainfall, and habitat that life learned to follow. When supercontinents break, the world lengthens its coastlines and multiplies its shallow seas, the tender sunlit shelves where primary producers thrive and ecosystems diversify into fine-grained mosaics. Rifting pulls the crust thin, faults step down, basalt fountains from fissures, and long, narrow seas form where once there were river valleys and sagging plains. New oceans open, mid-ocean ridges snake forward, as parallel hills of fresh crust. The ridge push and slab pull of plate dynamics redistribute strain around the planet. With more margins come more estuaries and deltas, more mangroves and seagrasses, more nooks where reefs can take hold and fish nurseries can spread. With more gateways come new current paths that carry heat into high latitudes or drain it away. At the same time, the volcanic outpourings that accompany rifting can build large, igneous provinces, broad plateaus of lava that release gases and warmth, altering climate for long intervals and leaving stepwise marks in carbon isotopes and sedimentary facies. Life navigates by adapting its ranges and habits. Coastal lineages split as barriers rise. Inland floras shuffle with shifting rain belts. Migratory routes stretch and fold as mountain shadows move and oceans invade lowlands. Even the thickness of crust and the elevation of continents play into sea level through the slow physics of isostasy and thermal state. Young, hot, oceanic crust rides higher, displacing water onto continents and making empiric seas that lap across interiors, while old, cold crust sinks and drops sea level, exposing shelves and stitching together habitats that were once separated by swathes of warm, shallow water. During supercontinent assembly, much oceanic crust is old and deep, and global sea levels tend to fall, spreading wide, erosional surfaces and broad river networks. During breakup, new ridges are abundant and young, pushing waters onto the continents and leaving behind packages of marine sediments full of fossils that later readers split to find the outlines of shells and the textures of ancient seabeds. These slow swells and ebbs of water are not mere backdrops. They determine where carbon is buried, where reefs can build, and how much sunlight falls through clear water onto platforms. Feedbacks that further influence climate and oxygen in the air and sea. Across all of these breaths, biodiversity follows a pulse that is part ecological opportunity and part geographic chance. When continents fuse, lineages that were separate meet and mingle, sometimes competing, sometimes hybridizing, sometimes occupying new niches created along mountain fronts and in basins caught between sutures. When continents part, Vicarians splits populations and sends cousins on diverging paths, building endemism on islands and along new coasts. The tempo is not uniform. Some groups proliferate in the shallow, warm seas that bloom during breakup. Others prosper in the broad interiors and along the orogenic belts forged during assembly. Extinctions and radiations ride these reorganizations, their shapes modulated by the longevity of seaways and the persistence of climatic belts, by the long baselines set by weathering rates, by the inventory of volcanic gases released during the quieter phases of rifting and the louder eruptions of flood basalts. The record keeps these stories unevenly, yet the pattern holds when read across many basins. Longers during stable arrangements, faster morphing during transitions, always with the planet's plate-scale geometry setting the key. Beneath the crust, the mantle's slow currents remember supercontinents in their own way. When a supercontinent sits for long enough, heat may pool beneath it because the insulating lid slows convective loss, and that pooled heat can prime the mantle for later plumes that weaken the crust and initiate rifting. Conversely, long-lived subduction along one margin builds cold slabs that sink deep and reshape convection cells. And those cells tug plates along new lines, sometimes drawing separate continents toward the same collision course, as if pulled by a conveyor that spans the whole mantle. Over cycles, large structures like the African and Pacific superplumes rise and fall, and the planet's magnetic and volcanic patterns respond in ways that add texture to the surface story. We feel these deep habits only by their quiet imprints: regional uplift preceding breakup, swells that carry volcanic chains, gravity anomalies that map dense slabs like shadows beneath the surface, each a hint of a vast circulation that sets the tempo for the continent's dance. For life on land, the placement of continents determines the routes of rain, and rain governs the architecture of rivers and soils, which in turn shape the mosaics of forests, wetlands, and grasslands. During assembly, long mountain belts create rain shadows that can persist for tens of millions of years, guiding the spread of drought-tolerant floras and the evolution of animals adapted to seasonal scarcity. During breakup, newly minted coasts host humid belts that creep inland, feeding coal swamps in some eras and peatlands in others, sowing the conditions for future carbon burial. On the margins of drifting continents, storms sweep shelves and then retreat, and storm-dominated deposits stack in rhythms that later let readers tune climate cycles. On the interiors, Aeolian sands cross and recross, their crossbeds keeping wind directions and strengths like the memory of a breeze pressed into stone. Each arrangement writes its own script of plant strategies: deep roots on uplifted plateaus, buttressed trunks in floodplains, needle leaves in cold, dry interiors, and animal movement: migrations along coastal corridors, highland passes used as cool bridges, valley strings that carry water and forage through dry seasons. In the sea, gateways are the hinges of quiet change. The opening of a passage like the Drake Passage around Antarctica allows circumpolar currents to develop that isolate a continent thermally, encouraging ice and changing sea level gently over long arcs. The closing of a seaway like the Isthmus of Panama redirects warm water, intensifies monsoons elsewhere, and splits marine populations into separate oceans that evolve apart. As supercontinents break and assemble, such hinges multiply and vanish, guiding nutrients and heat, shaping the balance between carbonate platforms and silicyclastic shelves, and influencing where oxygenated deep waters can form and spread. The chemistry of the ocean follows, with carbon and sulfur cycles adjusting to new burial patterns and redox states, leaving isotopic swings that line up across basins like distant clocks striking the same hour. Plankton communities respond in composition and size, altering how much carbon sinks to depth. Reef builders trade dominance as temperatures and saturation states drift. Fish and marine reptiles ride the prevailing paths, their ranges expanding and contracting with the breathing roots. Because the cycle is slow, its chapters overlap and hum along each other. There is never a clean start or stop, only gradients. A continent may be rifting in one sector while colliding in another, A sea may be opening at one end and narrowing at the other. A mountain belt may be eroding in its core while still rising at its edges. The cumulative effect is a patchwork world where local stories nest within global patterns, and life must navigate both scales at once. A lineage might find refuge in a basin that remains humid while the surrounding land dries, or travel along a coast that stays warm because a current hugs it even as the interior cools. An inland sea might concentrate salinity and close, leaving behind salt flats that reflect light and heat back into the local air. A newly opened strait might flood a marginal basin with nutrients and set off blooms that ripple through food webs. The unseen mega-event here is not a single episode, but the planet's habit of reorganizing itself, gradually but decisively, and each reorganization leaves enough quiet traces in rocks and fossils, in the way rivers stack their sands, and in the way shells arrange their isotopes, that we can follow the breath without ever needing to hear it drawn in. Imagine Earth's clock as a soft drum, its beat stretching ever so slightly from one dawn to the next, while the moon drifts outward by the width of a fingernail each day. Nothing sudden happens, yet across eons the rhythm changes our shorelines, our tides, and the daily lives written into ancient sediments. The mechanism is quiet. Tides raised by the moon and sun tug at the oceans and even, faintly, at the crust itself. Because Earth spins faster than the moon orbits, the tidal bulges lean a little ahead of the moon. Gravity tries to straighten that lean, pulling back on the bulge and forward on the moon. A whisper of rotational energy leaves Earth and slips into the moon's orbit. Earth's spin slows. The day lengthens by heartbeats, stretched to heartbeats, plus a breath. The moon climbs outward in a slow spiral, farther each year by centimeters. A pace you could measure with a ruler, if you had patience like stone. In the present, this exchange is tiny, but let it run for hundreds of millions of years, and the cumulative effect is a planetary metronome retimed. Ancient corals and bivalves kept daily growth lines that, when counted under a microscope, reveal years with more days, about 400 in the late Devonian. Each day shorter than hours by a couple of hours, each month shorter because the moon orbited closer and faster. Those lines are not theory, they are diaries etched in carbonate, recording tides and light the way a tree records seasons. Tides are not just heights of water, they are traveling patterns of energy, shaped by the basins they cross. The slowing of Earth nudges the pace of those patterns, and the changing distance to the moon shifts their strength. Meanwhile, continents move, and the ocean basins that host the tides retune like new shells placed over the same ear. Narrow seas amplify tides. Broad abyssal plains let them spread. Shelves, banks, and straits turn the energy into turbulence that warms water a whisper and pushes sediment grain by grain. In some eras, when continents clustered and shallow epiric seas spread across interiors, tidal energy dissipated efficiently in those wide, shoaling spaces, and tide ranges on some coasts likely swelled. In others, when deep oceans dominated and shelves were steeper, the same celestial tug translated into gentler coastal pulses. The result on land is a patchwork of tidal signatures through time, mud drapes and sand lenses stacked into rhythmic tidalites, bundles that track spring to neap cycles like soft barcodes, crossbeds with doublets that repeat every 2 weeks, herringbone patterns where current reversed predictably, in cores pulled from old deltas and drowned platforms. Those alternations tally the breathing of water in calendars that predate calendars. And when their spacing shifts up section, you can almost feel the system retuning as basins shallowed, gateways opened, and the drum of the day stretched a fraction longer. Life took its cues from these rhythms. On tidal flats in deep time, microbial mats rose and fell under cycles of wetting and drying, trapping silt by day and gas bubbles by afternoon sun, then lying quiet under nocturnal cool. Their laminated buildups, stromatolites, carry repeating textures that match tidal cadence where conditions were right. A biological clock pressed into rock. Burrows rise and fall through bedding with the patience of animals that timed their feeding to ebb currents and hid when flood returned. Trace fossils stack in paired sets that mark bi-weekly pulses. Reproductive cycles in many coastal lineages locked to lunar light would have had different timing when the month was shorter, a schedule that slowly retimed itself as the moon stepped outward and nights of maximum glow crept farther apart. Coral polyps laid down aragonite by day and by night in narrow increments. Bivalves added ridges through daily chemistry. Fish in tidal creeks schooled according to currents that reversed on clocks you could have set a net by. And in some intervals, the entire food web on shelves pulsed to the fortnightly beat of spring and neap, with turbidity, nutrient delivery, and larval dispersal easing and tightening, like a patient hand on a valve. Longer days did not merely stretch afternoons, they rearranged physiology in small, accumulating ways. Circadian rhythms, biochemical loops tuned to light and dark, entrained to the length of the day. When days were shorter, metabolic peaks fit into different windows, and as the day lengthened, those loops relaxed into new alignments. Plants that opened stomata to drink light and close against drought may have paced that dance differently under shorter photoperiods, changing growth rates and gas exchange in ways written in the microstructure of fossil wood. In shallow marine settings, photosynthesizers riding tides had different exposure times and depths. The balance between exposure stress and nutrient gain shifted with tiny changes in timing stretched over ages. Even predators that hunted by phase, using darkness or rip currents, rode schedules that drifted as lunar distance grew. A drift that ecosystems absorbed not by jerks, but by the steady substitution of behavior in new frames, the way a song can be transposed without losing its melody. The moon's retreat also couples to the planet's wobble. As Earth slows, its rotational bulge relaxes slightly, altering how precession, the slow conical sweep of Earth's axis, ticks along. Milankovitch cycles, those gentle variations in seasons driven by orbital geometry, keep their own long tempos, but tidal friction nudges the spacing subtly. The beat remains, yet its subdivisions shift by measures too fine for a single epoch to notice, and large enough for stacked strata spanning millions of years to reflect. In lake muds and shelf carbonates, where seasonal and orbital rhythms are preserved as light-dark couplets and bundled groups, astrochronologists count and tune those beats to reconstruct calendars of ancient time. Sometimes the fit improves when models include a slightly different length of day or precession pace, a reconciliation of celestial mechanics with the grain-by-grain ledger of sediment. In the background hum of energy budgets, tides matter as a global dissipator. The work they do as they rub against coasts, shoals, and the sea floor turns orbital and rotational order into tiny pockets of heat while stirring thermoclines and haloclines, breaking down stratification and lifting nutrients. In epochs when shallow seas were common, continental interiors drowned by high eustatic levels and warm, buoyant oceanic crust, this tidal stirring would have favored productive shelves, strengthening upwelling at embayments and sills, and sprinkling oxygen into otherwise sleepy bottoms. In epochs with fewer shelves and steeper margins, the same tidal energy would have traveled longer before spending itself, translating into different patterns of mixing, and downstream into a different map of where black shales could form under persistent oxygen lows. Those shales, rich in organic carbon, lock away atmospheric CO2 when buried. Thus, the softly changing drumbeat of day length and tidal strength participates, lightly but truly, in the slow carbon cycle, feeding back on climate by modulating where and when carbon is stored. The geomorphic fingerprints are everywhere once you know how to look. Ancient estuaries show point bars cut and filled in rhythms that match spring surges. Tidal inlet sands carry bidirectional sets that flip like pages every few decimeters. Marsh peats sandwich with crevasse splays in ladders set by fortnightly extremes. In Proterozoic and Paleozoic successions, tidal bundles sometimes preserve enough increments to estimate the number of days in a lunar month and the number of months in a year, an arithmetic confirmed by coral and bivalve growth lines. Those independent clocks, sedimentary, skeletal, agree within eras dictated by diagenesis and counting, and together they trace a curve from fast-spinning Earth, a nearby moon, to the slightly lazier pair we live with now. That curve is not smooth everywhere. Ocean basin geometry and continental positions modulate tidal dissipation efficiency, and thus the rate of lunar recession, so the outward drift likely varied, faster when broad, shallow seas were abundant, slower when deep oceans dominated. In the rocks, that modulation is hinted at by intervals that preserve especially clear tidal rhythms, and by models that fit modern physics to ancient maps and find resonant ages when certain basins would have boomed with heavy tides. Even solid earth tides, elastic flexing of the crust itself, add their faint mark. Repeated bending loosens and tightens fractures, changing permeability in ways that breathe fluids through rocks. In hydrothermal systems, that breathing may have paced mineral deposition by a fraction. In coastal aquifers, it opens and closes the pores that feed springs. On lava lakes and shallow magma chambers, it can modulate the rise of bubbles and the timing of quiet sloshes beneath a cooled skin. Over geological spans, the net effect is subtle, but it adds one more layer to the way the moon's slow retreat and Earth's slow sigh coordinate processes we often treat separately. Sediment laid down by water, crystals grown from fluids, gases exchanged through leaves and skin, larvae launched into currents that switch like a metronome from flood to ebb. Because this mega event is unseen, it is easy to ignore in favor of loud chapters, yet it is constant enough to be a frame. Extend it backward, and our earliest tidal flats felt a brisker tempo. Extend it forward, and distant tides will be softer still, days longer, months longer, until solar tides and geometry dominate the pattern differently, and the resonance of basins writes a new score across coasts that will be in places we haven't yet imagined. To live inside this change is not to notice it. To read it in stone is to recognize that every lamination with a wrinkle, every paired set of cross beds, every coral with lines so fine they look like whispers under light, is a tick of the same clock we sleep under. And while continents choose where to place the stages, this slow adjustment of time itself sets the tempo for the background music, the rise and fall that tells crabs when to forage, mangroves when to breathe, microbes when to trap a skin of silt. And over millions of years, that music shifts by a note, then another, until the same song is played in a lower key, and the shore, without noticing, dances to it. Imagine the air itself learning to breathe. At first thin and strange, the sky held close to the ocean's chemistry. Then, over ages, drifting toward a clearer blue as oxygen rose in slow tides that never made a sound but changed everything that could move or make a shadow. Early seas were rich with dissolved iron and sulfur, and microbes stitched energy from light and chemicals in ways that hardly resembled the metabolisms we know. Some bacteria began splitting water, releasing oxygen as a waste. At first, that oxygen vanished into the sea's appetite, rusting iron into banded iron formations that stack like quiet barcodes in ancient rocks. Silvery hematite and dull magnetite alternating with jasper tones, testimony that oxygen was present but busy tying itself up. The atmosphere barely noticed. Only when the sinks filled, when iron was mostly precipitated out of seawater and volcanic gases were balanced by burial of reduced materials, did oxygen leak past the ocean and begin to accumulate in the air. That rise is written in subtle signatures, sulfur isotopes losing their odd mass-independent patterns that only persist in oxygen-poor skies. Continental red beds staining because iron could now oxidize on land. Detrital grains of minerals once stable in rivers and deltas disappearing because oxygen weathered them before they could travel far. It was not a switch, but a long sunrise, and as the light strengthened, new possibilities drew breath. Oxygen arriving felt like both a gift and a hazard. For microbes adapted to anoxic worlds, oxygen was a toxin that could shred molecules. For others, it was a richer fuel, a path to far more energy per breath. Metabolisms reorganized quietly. Enzymes evolved shields and cleaners to handle reactive oxygen. Pathways appeared that tapped oxygen as the final acceptor in cellular respiration, pulling far more work from the same carbon. Inside eukaryotic cells, already a form of life built from mergers and partnerships, respiring symbionts that would become mitochondria, took up residence, turning oxygen and carbon into energy and water with an efficiency that would later power swimmers, burrowers, and much later, walkers. At the scale of entire oceans, oxygen peeled back the reach of purple and green sulfur bacteria that had thrived in sunlit, sulfide-rich shallows, and pushed the chemocline, the invisible line separating oxygenated from anoxic waters, downward. The sea began to stratify in new ways. Deep basins sometimes remained dark and sulfurous, while shelves brightened enough to support food webs tied to oxygen breathing. In sediments, new niches opened as animals capable of tolerating or requiring oxygen began to burrow, mixing layers that had once lain sharp and laminated, altering how carbon and nutrients were stored and recycled. That first great rise did not settle immediately. The planet felt and adjusted through feedbacks that moved on million-year scales. As oxygen nibbled at methane in the air, a potent greenhouse gas made by microbes, global warmth slackened, ice advanced, reflective surfaces spread, and some models argue that the planet slipped into long, severe glaciations in which ice reached low latitudes, snowball episodes that, if they occurred as deeply as the rocks suggest, would have tested every metabolism and habitat. Glaciations scoured continents, grinding rocks to flour, when the world thawed, weathering flushed ions into the sea, boosting nutrients that fed blooms, and perhaps spurred further oxygen production, while carbonates precipitated in cap sequences that drape above glacial deposits like pale blankets. On land, oxygen's edge gnawed at sulfide minerals, sending sulfate to the ocean. In the sea, more sulfate supported sulfate reducers in the deep, changing the balance of sulfur isotopes recorded in pyrite and gypsum. The whole cycle, oxygen up, methane down, ice up, weathering up, nutrients up, traced a set of long commas in geochemical records, a grammar of patient cause and effect that never needed a headline to be decisive. Later, another oxygen step seems to unfold, not as dramatic in a single moment, but pronounced across many lines of evidence. Trace metals like molybdenum and uranium become more abundant in sediments in patterns that imply more oxygenated waters. Biomarkers of plankton and algae shift. The nitrogen cycle tunes itself toward pathways that require oxygen, like nitrification and the full loop of denitrification, changing how easily life could fix nitrogen and how abundant it could become. In that rising backdrop, eukaryotes diversify in form and habit. Cells grow larger, ornamented, and specialized. Algae bloom in new architectures. The first animals appear as soft impressions in ediacaran beds, quilted and fronded, grazing and breathing in worlds where oxygen had finally become abundant enough to support bodies that could manage tissues through diffusion and simple circulation. When animals learned to burrow deeper and more persistently, they oxygenated sediments by mixing them, a quiet revolution that allowed different chemistries to prevail just below the sea floor. That mixing reduced the preservation of softly laminated mats that once recorded every ripple and increased the prevalence of mottled, bioturbated fabrics, a blanket of evidence that life had entered the substrate and changed the rules of storage for carbon, phosphorus, and sulfur. Oxygen also lifted a shield overhead. As ozone accumulated in the upper atmosphere, a product of oxygen reacting under sunlight, the surface received less ultraviolet radiation, easing the stress on DNA for organisms nearer the light, and perhaps making shallow waters, and later damp land surfaces, more hospitable. Fires became possible only once oxygen rose past a threshold. Charcoals appear in the record in quantities that wax and wane with atmospheric oxygen. And the widespread coals of the Carboniferous are not just buried plants. They are a chemical echo that oxygen had climbed high enough for wood to burn, and for that burn to leave crimson and black traces. Fires in turn fed back on ecosystems and climate by clearing, by oxidizing, by shaping plant strategies and fuel loads. They also crafted thin lenses of ash and heat-altered minerals that now help readers mark time, elate time in layers with magnetic and chemical signatures. In forests and swamps, plants themselves nudged oxygen by inventing lignin, and then, as decomposers took time to catch up, burying organic carbon faster than it could be oxidized. Each gram tucked away spared a gram of oxygen to linger in the air, and the balance rose. None of these steps was uniform across the globe. Shallow shelves under trade winds oxygenated sooner than deep-silled basins. Restricted seas sometimes went euxinic, anoxic, and sulfidic, even when open oceans held more oxygen. Upwelling margins oscillated with climate, nourishing blooms that sank and stripped oxygen from underlying waters in pulses. These spatial patchworks make the oxygen story feel like a quilt. Bright patches growing and linking, dark patches shrinking and then returning, always with currents, nutrients, and topography dictating local fates. In some intervals, large igneous provinces bled CO2 and other gases into the air for long stretches. Warmth, weathering, and nutrient delivery shifted, and oxygen-rich shallows could falter, while deeper waters lapsed back toward anoxia. The record keeps these hesitations as black shales rich in organic matter, as metal enrichments that track oxygen-poor conditions, as sulfur isotopes that drift in patterns that only make sense if the deep sea regularly lost breath. Yet the long trend climbed. More habitats for aerobic life, more complex food webs, more niches for animals that moved, grazed, built, and filtered. For bodies, oxygen writes constraints that feel like design. Small forms live by diffusion alone. Larger forms need folding surfaces, circulations, or both. Muscles working steadily demand oxygen delivered and waste removed on a schedule. Nerves and senses require consistent chemistry to signal and reset. As oxygen rose, those constraints loosened a little, and the feasible space for body plans widened. Thin skins could thicken, layers of cells could collaborate, predators could sustain bursts, builders could cement, reef frameworks could become more elaborate, with pumping and filtering communities bound together by carbonate that precipitated more readily in certain chemistries. In the water column, planktonic food chains lengthened. In sediments, oxygenated surfaces supported more burrowers and grazers. In space, the water column became a three-dimensional stage where size, speed, and behavior could escalate. Not every innovation waited on oxygen. Many sorted themselves out in anoxic worlds too, but the long availability of oxygen made more combinations durable, more experiments survivable, and more feedbacks between behavior and environment possible. On land, oxygen narrated its own chapter in partnership with plants. As rooted life spread, soils deepened and stabilized, weathering rates rose, and the delivery of phosphorus and other nutrients to the sea changed, sometimes boosting marine productivity and, by extension, oxygen production. The stomatal densities on fossil leaves, the tiny pores that plants used to breathe, shift with CO2 levels and indirectly hint at oxygen's complement. Coal balls preserve tissues in such detail that the proportion of woody to soft tissues can be read alongside spores and pollen to trace how forest architectures, fuels, and fire potentials evolved. Insects, liberated by plentiful oxygen and dense vegetation, grew to sizes that seem improbable under modern air. Their stature implies oxygen high enough to saturate tissues, even in large tracheal systems, and the charcoal record agrees, suggesting that fire patrols the same times and places as these giants walked and flew. Later, as climates cooled and swamps retreated, oxygen likely eased back from carboniferous highs, with fire and insect size following. Chemically, oxygen's ascent altered the availability of trace metals that enzymes need. Molybdenum, copper, zinc, iron all shift in solubility and distribution with redox state. Nitrogen fixation, which requires large investments of energy and metal cofactors, and nitrification and denitrification, which require stepwise aerobic and anaerobic corners, found new balances under different oxygen regimes. Phosphorus, often the limiting nutrient, cycled through sediments differently as iron oxides formed in oxygenated waters, binding phosphate in ways that either locked it away or returned it under anoxic episodes, creating feedbacks where oxygen oscillated in pace with nutrient traps and releases. These quiet adjustments wrote long-term carrying capacities for ecosystems, how much productivity shelves could maintain, how resilient upwelling zones were to small climatic nudges, how quickly deep waters could reoxygenate after stagnation. In turn, those capacities set the background against which evolutionary radiations and extinctions played out, not as causes alone, but as the stage that made certain dramas possible and others unlikely. In the fossil record, oxygen's fingerprints multiply when you learn their shapes. Iron formations fading as the first rise succeeds. Red beds blooming on land. Pyrite sulfur isotopes losing their ancient oddities. Charcoal appearing in volumes that wax and wane. Bioturbation textures replacing delicate laminations. Reefs thickening with more active cementation and more animal-built frameworks. Animal traces, tracks, burrows, borings, invading sediments once ruled by microbial carpets. In the geochemical archives, carbon isotopes swell and dip as organic burial changes. Molybdenum and uranium enrichments mark oxygen-poor basins that expanded and shrank. Chromium isotopes in weathered soils hint at oxidative processes on land. Rare earth element patterns in carbonates track redox and water masses. Each proxy is cautious by itself. Together, they sketch that long, slow curve upward, stepped and sawtoothed, with plate motions, eruptions, and evolving life feeding it and feeding from it. The unseen mega-event is not merely that oxygen rose, but that it did so in packages separated by long plateaus, with each package coupled to tectonics, climate, and biology in loops that reinforced or damped the rise. Supercontinents insulating manjatonk, and then rifting, changed weathering and nutrient delivery. Large igneous provinces tuned CO2 and warmth, shifting stratification and oxygen demand. Evolving producers, cyanobacteria, algae, then land plants, changed the efficiency and place of carbon burial. Animals changed sediments and water clarity by burrowing and filtering. Fires rearranged landscapes and emissions. And through it all, the chemistry of the air and sea set what bodies could be built, how large they could grow, how fast they could move, and how far they could penetrate into the dark. The sky we breathe now is not a default. It is a long collaboration between rock, water, and life, negotiated in whispers across stone that still keeps the minutes in thin bands and tiny grains, so that if you hold a sliver of ancient reef or a shard of banded iron under a lamp and tilt it, you can see not just color and sheen, but a record of breath thickening until it could carry wings, songs, and the quiet sigh of waves under a blue that once did not exist at all. Picture heat rising through the mantle like a broad, patient exhale, spreading under the crust until rock softens, thins, and finally gives way in long fissures. What follows is not a single volcano, but a province. Thousands of vents, sheets of lava, pouring quietly across landscapes, stacking into plateaus that can blanket a subcontinent in stone. These are large, igneous provinces, slow storms of basalt that may erupt pulse by pulse over hundreds of thousands to a few million years, each pulse adding new warmth and new gases to air and sea. The lava itself advances at walking pace when it meets gentle ground, cooling at the surface into ropey skins and beneath into thick jointed columns that crack like drying mud, but on a scale of cliffs. Successive flows weld into steps, and later rivers cut canyons through them, revealing a library of dark pages. Between pulses, soils develop on warm rock, plants creep back, and then another sheet arrives and resets the surface. A cycle recorded in thin, baked horizons and charcoals trapped beneath tips of advancing flows. Beneath the ground, the same heat sends dikes and sills like black ribs and shelves through sedimentary basins, where these intrusions bake organic rich shales, coals, or evaporites. They distill carbon dioxide, methane, and halogens from the country rock, adding to the gases rising directly from magma and turning the province into a broad, persistent source that the sky must absorb. The atmosphere listens in two registers at once: sulfur dioxide and ash from the more vigorous pulses climb into the stratosphere, where they form hazes of sulfate that reflect sunlight and cool the surface, for seasons to years. These veils blur the sun, nudge monsoons, and can trim growing seasons across wide belts. Carbon dioxide, by contrast, accumulates on longer scales, thickening the planet's blanket, so that after the sulfur fogs settle and rains wash the aerosols from the air, warmth lingers and creeps. The balance between short, cool veils and longer, warm blankets is delicate and changes with the vigor of pulses, the height of injections, the latitude of vents, and the background state of the climate system. Oceans respond with their own patience. Warmer air slows the overturning of surface and deep waters. Stratification strengthens, and oxygen struggles to reach depth. Nutrients from land increase as fresh basalt weathers rapidly, releasing phosphorus, silica, and iron that fertilize surface waters. Blooms grow, sink, and, if deep waters are low in oxygen, rot in ways that strip even more oxygen, setting shelves and marginal seas on a path toward quiet darkness. In sediments, this appears as black shales rich in organic carbon. In the chemistry, as excursions in carbon isotopes, as enrichments of redox-sensitive metals, and as mercury spikes, fine ashfalls of the element that travels with volcanic plumes and settles into muds as a tracer of prolonged degassing. Geologically, these provinces often open new crust as continents begin to part. At triple junctions where rifts meet, swarms of dikes radiate for hundreds to thousands of kilometers, each a frozen channel that once fed surface flows. On maps, they look like veins on a giant leaf, and their directions tell how stress stretched the plate when the lava ran. The first pulses sometimes precede full rifting by a beat, lifting and doming the crust so that rivers reverse and lakes form along gentle swells. Later, pulses coincide with seafloor spreading and thick wedges of seaward-dipping reflectors, layered basalts, build the edges of new oceans like ramps into deep water. In this way, a province is both a cause and a companion of continental breakup. It supplies heat and weakness to help plates part, and it records the moment in thick, simple sequences that later readers can trace at the margins of basins and along the shoulders of rifts. When sills invade evaporites, salty layers of ancient seas, they can bleed chlorine and bromine-bearing gases that, in the air, affect ozone chemistry. When they boil water in coal measures, they release thermogenic methane that adds to greenhouse forcing. When they contact carbonates, they liberate CO2 directly. The result is a spectrum of gas recipes that varies from province to province, depending on what rocks the magma touched, making each event its own slow accent in the climate story. On land, fresh basalt is a paradox for life. At first sterile, hot and black, yet quickly weathered into mineral-rich soils once water and air do their quiet work. Basalt weathers faster than most silicate rocks, drawing down atmospheric CO2 as carbonic acid reacts with calcium and magnesium to form bicarbonate, which rivers deliver to the sea where carbon is locked into carbonate minerals. This is the planet's long thermostat at work, and after the warming pulses from degassing, the spread of reactive rock can hasten the return toward cooler states, especially under warm, wet climates that accelerate chemical weathering. So river loads change, clay minerals accumulate, and the color of water down from new plateaus carries more suspended silt after storms. Lakes dammed by flows strand and fill. Floodplains are diverted and reset. Groundwater finds new paths along joints and between flows. Springs emerge where permeable and impermeable layers alternate, and plants, once established on the new soils, knit the surface and speed the weathering with roots and acids, an exchange in which rock and life partner to change the air, a little at a time. In the sea, the fertilization from basaltic weathering reinforces patterns set by warmth and circulation. Silica feeds diatoms, iron feeds plankton in high-nutrient, low-chlorophyll regions. Phosphorus pushes production on shelves and in restricted seas. Where circulation lags, these gifts deepen oxygen debt. Where winds and gateways keep waters lively, they seed blooms that export carbon to depth without starving the bottom entirely. The line between helpful and harmful is thin and moves with geography. The same nutrient pulse that builds reefs on one margin under clear, well-mixed water can tip a silled basin into anoxia elsewhere. Black shales preserve this difference, laminated, dark muds in one place, bioturbated, lighter sands and silts in another, both linked to the same distant plateau by river and aerosol. In the chemistry of shells, boron isotopes whisper of acidification when CO2 rose quickly. In stomatal patterns on fossil leaves, the breath of plants hints at elevated CO2 during the warm phases. In osmium isotopes, the ratio shifts toward mantle values when weathering of basalt and volcanic inputs dominate river loads and dust, marking the timing and intensity of eruptions, even if the flows themselves lie far from the core you are reading. The timing of pulses within a province matters because biology has its own tempos of resilience. A short, sharp cluster of eruptions that injects sulfate high and throws a quick veil may stress communities but allow recovery between veils. A drawn-out train of pulses that keeps CO2 high for hundreds of thousands of years can move climate zones, dry interiors, and warm seas, enough to rearrange biomes and food webs in ways that last long after the last lava cools. On land, belts of aridity widen or migrate. Forests give ground to open habitats. Fires change in frequency and intensity as fuels and humidity shift. Migration routes bend along mountain shadows cast by the plateau itself. In the water, carbonate platforms drown or retreat to refugia when acidification and warmth push saturation states below comfort. Reef builders trade off. Some corals cede to sponges, some sponges to microbialites, and the architecture of habitat changes for the neighbors who hide and forage among them. The link is neither instant nor simple. It is a suggestion pressed gently into many pages at once, the kind of suggestion you only see when you stack those pages and run your thumb along their edges. Because the message is quiet, geologists look for its punctuation marks. Thin ash layers fallen far from vents carry crystals datable by uranium-lead clocks, pinning ages in muds and limestones that otherwise lack clear anchors. Mercury peaks bloom in marine sections worldwide at horizons that align with major pulses of degassing, and when paired with carbon isotope excursions, global swings in the ratio of carbon-13 to carbon-12, tied to how much organic carbon burial or volcanic carbon input changed. They sharpen the outline of the province's climate voice. In shallow, wave-worked sands, pillow lavas, and hyaloclastite breccias note where flows met water. In red-baked contacts beneath flows, charred plant fragments trace ecosystems interrupted and preserved. In the interiors of thick flows, columnar joints and vesicle pipes sketch cooling and degassing histories like fingerprints. Dike orientations map stress fields. Sill thicknesses measure time in cooling units. Chilled margins record the order in which intrusions arrived. Baked aureoles around sills in coals and organic shales preserve delicate minerals and gases that tell the temperature and duration of heating. Altogether, these quiet tokens let readers reconstruct a process too big to see in one outcrop and too slow to feel in a human moment. After the last lava, the plateau remains as a long memory. Its mass loads the crust and flexes it. Its weight and the density contrast with surrounding rocks can deflect rivers and create forebulges and sags that persist for millions of years. Its hardness resists erosion so that highlands linger where once was a field of fire. Its stair steps invite waterfalls where streams leap from flow top to flow top. In some climates, the tops of flows host thin, fertile soils that support grasslands. In others, jointed columns weather into cliffs and talus that host sparse, specialized floras and faunas. Caves form in flow interiors along weakness plains, trapping sediments and bones much later, giving future readers sheltered archives set into stone that was born of speed and cooled into patience. From orbit, satellite data trace magnetic stripes and gravity anomalies that match the province's hidden bones. At the surface, lichens and grasses fill cracks that were once conduits for glowing melt. The scale shift, a reminder of how thickly time lays its hands on the same geometry. The whisper in the sky is not only about warmth. Halogen-bearing gases from some provinces can thin ozone for a while, letting more ultraviolet light reach the surface and raising stress in organisms near the light, especially in shallow waters and on land where shade is scarce. Nitrate anomalies in sediments and damage patterns in spores and pollen hint at such episodes where they align with other signals. Dust stirred by drying belts after warming carries iron far out over oceans, fertilizing in a different wind-borne way. And when it falls, it adds its signature to sea muds, telling of aridity downwind of the plateau long after the lava stopped. Rains that fall on freshly cooled flows pick up different ions than rains on granite or sandstone. Those waters percolate to aquifers with slightly shifted chemistries, and springs record the change in tufa, travertine, and the isotopic fingerprints of the carbon they lay down. In lakes trapped behind flow dams, varbs, annual layers, grow and count quietly, and sometimes they span centuries that bridge from the last glow of basalt to the first common shrubs, keeping a ledger of how quickly the land resumed ordinary seasons. Over very long spans, the province becomes part of the carbon cycle's memory through weathering. As rivers grind and dissolve its minerals, They carry calcium and magnesium that end up in marine carbonates, turning ephemeral volcanic CO2 into limestone and dolostone that sink into the crust at subduction zones and return as gas again only after long, looping journeys. The net arc is a pulse and a drawdown. Degassing warms and acidifies, weathering cools and neutralizes. Life bends with the pulse and exploits the drawdown, making more reef, more shell, more burial where conditions allow. Seen across several provinces in a deep time record, these arcs form a ragged cadence in which each event differs in strength and flavor, but all speak the same language of stone to air to stone, a grammar of exchange that does not need catastrophe to be consequential. If you stand on a basalt cliff late in the day, you can feel a small version of the cycle as the rock releases the heat it stored at noon. The air warms a breath around your hands. Swallows ride the lift. A thin sound comes from a stream cutting along a flow boundary where the rock is weaker. That stored warmth is to the sun what the province's CO2 is to climate, a buffer and a lag. And just as the cliff will cool overnight and warm again tomorrow, the climate response to a province has its own phases and returns, never perfectly repeating, always influenced by the shape of basins, the position of continents, and the state of the biosphere at the time. The unseen mega-event here is the persistence, how a mantle surge becomes a surface of stone, how that stone speaks to clouds and rivers, how clouds and rivers answer with weathering and delivery, how seas answer with blooms and burials, and how the echoes of each pulse can be read in soft bands and delicate chemistries long after the last flow hardened into steps that a river now descends in small, steady falls. Imagine the ocean as a layered boards. Breath, cool, heavy waters sliding along the sea floor in the dark. Lighter, sun-warmed waters drifting above, bright with plankton and wind. And between them, a soft boundary that can rise and fall like a sleeping chest. When that boundary shoals and the deep grows still, the world feels it slowly. Oxygen thins at depth. The sea keeps its own exhale, and habits from shoreline to open ocean adjust, one small choice at a time. The engine behind the layers is part temperature, part salt, part geography. Winds push surface waters away, and upwellings replace them with cold, nutrient-rich flows. Polar air chills brine until it sinks, dragging oxygen into the dark. Evaporation and rainfall write salt maps that help decide where the heavy water forms. Narrow gateways steer currents like valves in a quiet machine. Over millions of years, the settings on that machine shift as continents drift, as mountains rise and weather down, as ice locks fresh water on land or returns it to the sea. Sometimes the ocean turns over briskly. Sometimes it stratifies, its deep lanes growing sluggish, and the difference writes itself into mud one grain at a time. When overturning wanes, oxygen has farther to go and more work to do. Organic particles snow from the bright zone above, the soft remains of plankton, the fecal threads of grazers, the delicate skeletons made of calcite or silica. And as they sink, bacteria harvest their carbon, using what oxygen is present until little is left. If fresh, dense water no longer sinks regularly to carry new oxygen downward, large parts of the deep slip into low oxygen states. Along continental margins, oxygen minimum zones spread and thicken. In restricted basins with sills, waters can go fully anoxic, and in some intervals even sulfidic, accumulating hydrogen sulfide in the quiet dark. On the seafloor, worms and small crustaceans retreat. Bioturbation slackens. The thin laminations of seasonal settling remain sharp because nothing mixes them. Black shales grow, laminated, organic-rich pages that later readers will split to find leaf-like films, tiny shells, and the chemical signatures of a sea that held its breath. These oceanic anoxic events are not single moments, but intervals, often paced by the planet's long orbital cycles and amplified by the slow background of plate motions and volcanic gases. They arrive differently in different basins and leave behind patterns that match local sill depths, winds, and freshwater input. The chemistry of these episodes moves in gentle loops. Warmer climates and higher CO2 can strengthen stratification by warming the surface and freshening it with rain, keeping dense water from forming. At the same time, weathering on land quickens and delivers phosphorus, silica, and iron to shelves and upwelling zones, fertilizing blooms that increase the rain of organic matter. The sinking flux draws down more oxygen and tips margins deeper into low oxygen states. In anoxic conditions, iron that would have bound phosphate in sediments can no longer hold it. Phosphate leaks back to the water column, where it feeds more blooms, a quiet, positive feedback that helps sustain the low oxygen state. Nitrogen cycles retune. Denitrification and anemox strip fixed nitrogen from the water where oxygen is scarce, favoring nitrogen-fixing cyanobacteria that can replace the loss. And in that trade, the isotopic fingerprints of nitrogen drift to heavier values that later show in kerogens and shells. Sulfur cycles, too, leave marks as sulfate reducers flourish in dark sediments and waters, producing sulfide that reacts with iron to form pyrite, shaping sulfur isotope patterns that can be matched from shelf to shelf. In the trace metals, molybdenum and uranium enrich in anoxic muds, their concentrations rising and falling with the reach of oxygen-poor waters, a quiet gauge that calibrates how far the shadows spread. Plankton communities respond with shifts that echo through food webs and sediments. In warm, nutrient-rich surface waters, some groups bloom, coccolithophores making chalky plates, diatoms weaving glass. In more acidic or undersaturated waters, calcifiers thin their shells or retreat to refuges, and the depth at which calcite dissolves, the lysocline, shoals, lifting the carbonate compensation depth so that fewer calcite tests survive to the sea floor. In the mud, this shows as intervals poor in carbonate and rich in organic matter and silica. In foraminiferal assemblages, as switches from thick-walled species to thin-walled or agglutinated forms that glue sand together when carbonate is scarce. In boron isotopes in planktonic shells, as hints of lower pH when CO2 rose faster than buffers could keep pace. Radiolarians, with their glass frameworks, sometimes flourish where silica is plentiful, and their rain builds cherts in deeper basins. Dinoflagellate cysts and organic-walled microfossils wax and wane, their counts tracing productivity pulses and salinity changes tied to monsoons, river plumes, and straits that open or close. Gateways and winds guide the grand retuning. Open a passage at high southern latitudes, and a circumpolar current can spin up, isolating Antarctica, encouraging ice, and redirecting deep water formation. Close the narrow seaway in the tropics, and salinity contrasts sharpen between oceans, strengthening or weakening, overturning elsewhere. Lift a shallow sill, and a marginal sea flips from well-ventilated to stagnant with a step that shows clearly in laminations and metal enrichments. On shorter timescales paced by orbital cycles, monsoons breathe stronger or softer, freshening surface waters seasonally and spreading thin, low-density lenses that cap the sea. In such capped basins, sapropels, dark, organic-rich layers, accumulate periodically, as in the Mediterranean, where summer insolation peaks once favored river plumes and stratification, dimming the bottom and writing dark bands between lighter marls. Each band is a quiet notation of climate rhythm tied to precession, and stacked together they form a book of breaths that astrochronologists can count to reconstruct calendars of change. Even when deep waters are not fully anoxic, small shifts in mixing matter, oxygen minimum zones that thicken by only 100 meters can alter migration corridors for fish and invertebrates that ride daily vertical movements. Denser layers pressed a little deeper can keep nutrients trapped below the reach of surface light, starving a region that once bloomed. Upwelling jets that shift laterally by a few tens of kilometers can move productivity and fog belts along coasts, redirecting guano-making seabirds, kelp forests, and the archaeological scatter of human fishing geese that later dots coastal terraces. On the seafloor, a narrow expansion of low oxygen at the sediment-water interface replaces a lively, mixed fabric with a thinly laminated one, and the change persists even if average oxygen values differ by only a small fraction. In this way, the ocean's gentle adjustments accumulate into scenes that look different and feel different to their inhabitants, without ever announcing themselves with a single loud moment. The isotopic diaries match the textures. Carbon isotopes often show positive excursions during intervals of widespread organic burial. As more light carbon sinks and is sequestered in black shales, the remaining carbon pool grows relatively heavier, and shells and carbonates record that shift. When the burial eases or volcanic carbon enters, the ratio falls back. Strontium isotopes in marine carbonates drift with the balance of weathering between young basalts and old continental rocks. And during times when basaltic provinces weather quickly and deliver ions, the signal leans toward mantle-like values. Osmium isotopes in fine sediments trace similar inputs, responding rapidly because osmium cycles quickly compared to strontium. Chromium and cerium anomalies in iron-manganese deposits and carbonates hint at redox at the seafloor and in the water column. Thallium isotopes in black shales respond to the extent of manganese oxide burial, itself tied to oxygen availability. None of these clues shouts by itself. Together they lay a lattice that holds the shape of circulation changes gently in place. On continental margins, the story is intimate. River deltas swell and pulse with climate. Floods freshen shelves and enhance stratification. Storm seasons stir the upper tens of meters and then leave, letting particles settle into thin couplets that carry the memory of seasons stacked like pages. Where hypoxia creeps shoreward, benthic communities simplify, burrow diameters shrink, the depth of bioturbation thins, shellbeds record more attrition and less in-place life. Yet pockets of oxygenated refugees persist in topographic highs and near-persistent eddies, and these refugees serve as seed banks for recovery when mixing returns. In cores, the alternation of laminated and mottled intervals marks that give and take with a subtlety that suits a sleep channel, the same bed form humming under slightly different air. Over very long arcs, turning the ocean over or letting it fall still connects to mountains and CO2 in ways that fold back on climate. Efficient overturning draws oxygen deep, encourages widespread burial of organic matter in well-ventilated margins without letting anoxia claim too much shelf, and the burial sips CO2 from the air. Sluggish overturning encourages black shales in restricted places and can bury even more carbon for a time. But if stratification spreads too widely, nutrient traps and a stressed biosphere can lower productivity and soften the sink. Weathering on land supplies alkalinity that keeps the ocean's carbonate system robust. When weathering falters, the ocean becomes more sensitive to CO2 pulses. When weathering strengthens, the buffers hold longer. The result is a set of slow feedbacks that drift toward balance after each nudge, and in that drift, the sedimentary record records not only the nudge, but the return. For those who read these chapters, certain signals have become familiar comforts. A sudden rise in barium and a dip in bioturbation say productivity pulsed while oxygen thinned. A horizon rich in spheroidal mercury grains suggests faraway degassing that might have warmed the surface and strengthened stratification. A bouquet of biomarkers, isorenieretin from green sulfur bacteria, for example, says sulfidic conditions reached lighted waters in that basin for a while. Foraminifera living at the surface versus in the thermocline trade places in samples when the boundary shoals. Heavy oxygen isotopes in benthic shells lift or fall with ice and deep water temperature. The coiling direction in some planktonic species tracks temperature bands and currents. Each of these is a murmur from a different depth, together a chord that says the ocean's breath was longer or shorter then, and life arranged itself accordingly. Even the floor of the deepest basins keeps the tempo in small ways. Where overturning is vigorous, manganese nodules and crusts grow slowly over millions of years, accreting metals from oxygenated bottom waters. Where oxygen drops, growth slows, and surfaces darken differently. In contourites, sands and silts shaped by deep boundary currents, grain sizes and bed forms whisper how steady and strong those currents were. When circulation reorganizes, the pattern drifts, and cross-sections preserve that drift as foresets at scales of centimeters and meters that, when logged, become maps of invisible rivers at the bottom of the sea. Turbidites that pulse down slopes after storms, and earthquakes carry different signatures depending on whether bottom waters were clear or hazy with plankton rain when they fell, and the fine tops of those beds retain the chemistry of the day the layer settled. All of this is quieter than a meteor and slower than a mountain's rise, and yet it moves shorelines of oxygen that millions of gills and siphons depend on. It resets where reefs can keep their skeletons and where they must thin. It chooses which shelves become black pages and which remain light and mixed. It tucks away carbon for future climates or returns it. It threads migrations along invisible plains that only instruments can see and only sediments remember. To imagine the ocean turning over or holding still is to imagine the planet's single largest organ changing its heartbeat by a fraction, and every creature listening, adjusting sleep, feeding, spawning, drifting, and burrowing to match a rhythm that writes itself into stone in lines so fine you need a lamp and a slow breath to read them. Imagine a mountain range rising so slowly that forests have time to climb with it, rivers to carve new stairs, and the air itself to thin and cool in a way that changes the flavor of rain. What looks like stone stacked against the sky is also a thermostat, a quiet dial the planet turns with uplift and weathering. When plates converge, crust thickens and buckles. Rocks once buried find themselves tilted toward light. Fractures open pathways for water and frost, and peaks shoulder into winds that wring moisture from passing air. Every grain loosened from a ridge and carried down a slope is a small exchange with the atmosphere. Carbonic acid, rainwater holding a breath of CO2, seeps into cracks and reacts with silicate minerals, trading carbon in the air for bicarbonate in streams. Those ions go to the sea, where they help build carbonates that fall, lock away carbon, and let the sky breathe a little easier. The faster a mountain sheds grains, under warm, wet monsoons or in freeze-thaw seasons, the stronger this drawdown becomes. And over millions of years, the balance can lean toward cooler climates simply because rock was lifted high and given to water and roots to work on. Weathering is not just chemistry, it is texture and time. Freshly uplifted rock has sharp faces and dense fabrics that resist, but joints and foliation give water an opening. Frost wedges blocks and makes tailless fans that creep and collapse. Roots pry with patient force, feeding acids into micro-fractures. Lichens and microbes colonize, etching films into minerals. Soil thickens in pockets and thins on spurs, always on the move. On south-facing slopes in mid-latitudes, snow melts sooner, and the season of reaction grows longer. On cloud-bathed ridges, mists keep surfaces wet enough for reactions, even when rain is brief. In tropical mountains, warm temperatures and heavy rains carve deep weathering profiles, laterites and saprolites, where iron reddens and clays build. In high cold ranges, chemical reactions slow, but physical weathering and glacial grinding create fresh mineral surfaces faster than lowlands could hope to, feeding rivers with fine rock flour that dissolves quickly once it reaches warmer valleys and the sea. Each climate writes its own rhythm onto the same uplift. And the sum of these rhythms is a steady leak of bicarbonate and cations that tilt carbon from air to ocean. Mountains bend winds and monsoons, and the rains they summon sculpt both sides differently. On the windward side, air rises, cools, and spills its water in layered storms that feed forests, soils, and thick, weathering mantles. On the leeward side, a rain shadow dries the land, sparsening vegetation and slowing chemical attack, even as temperature swings and dust-laden winds keep surfaces in motion. Rivers on the wet flank braid and avulse across fans, then focus into canyons. Slack water pools trap fine sediment. Terraces step down valley walls where climate pulses were recorded as alternations of build and cut. In each step, gravels and silts hold leaf imprints, pollen, and charcoal that mark the changing assembly of plants as elevation bands shifted with cooling. On the dry flank, ephemeral streams flash and fade, salts bloom in flats, Aeolian sands move in sheets and wedges, and yet even here, rare storms and dew feed slow mineral change. The thermostat effect depends on both faces. Wet side weathering pulls CO2 down efficiently. Dry side erosion exports chunks that expose new surfaces when they roll and grind. Both together keep the system ventilated. As uplift continues, glaciers may take their tools from the cabinet. Snow lines step down when climate cools, or mountains rise into colder air. Cirques grow, horns sharpen, and U-shaped valleys guide ice tongues that pluck and abrade bedrock into silt-sized flour. This fine powder, rock flour, turns alpine streams milky and feeds fjords and proglacial lakes with suspended grains that settle into varves, counting seasons with paired light and dark layers. In the presence of liquid water downstream, these freshly ground minerals dissolve rapidly, reacting with CO2-enriched waters to accelerate the silicate weathering feedback. At the same time, ice can shield high bedrock from rain for a while, pausing chemical reactions beneath. When it retreats, the newly exposed surfaces are as reactive as fresh fracture faces, and colonizing microbes and plants find a blank canvas to paint with acids and roots. Meltwater carries not only ions but nutrients, phosphorus from apatite, iron from mafic minerals that fertilize downstream lakes and coastal waters, promoting blooms that capture more carbon and draw oxygen into fresh circulation. Each glaciated valley is a soft pump, its pulse aligned with the seasons, but its long-term stroke tuned to uplift and climate. Weathering does not simply remove, it transforms. Feldspars turn to clays, micas unweave, olivine and pyroxene surrender cations readily. Carbonates dissolve and reprecipitate in karst pockets. Sulfides oxidize to sulfates that scrawl bright streaks across cuts. The products matter. Clays change soil structure and water-holding capacity. Iron oxides bind phosphorus that might otherwise run free. Dissolved silica regulates diatom growth in the sea. Calcium and magnesium shipped in solution determine how much carbonate can precipitate. In the isotopes, these transformations leave signatures, strontium ratios leaning toward radiogenic values when old continental crust dominates weathering, toward mantle values when young basalts and ophiolites are ground. lithium and magnesium isotopes shifting with silicate alteration intensity, osmium in sediments pulsing toward mantle at times of rapid uplift and erosion. These chemical diaries are the mountain's correspondence with the ocean, and together they reveal not only how fast rock is being worked, but which rocks are at the workbench. As ranges rise, they also sag under their own mass, and the lithosphere flexes, creating foreland basins that catch sediments like open hands. These basins are where much of the weathered load comes to rest. Their thicknesses and faces record the tempo of uplift and erosion. River deltas push seaward in tongues, coal swamps spread in humid phases, lacustrine shales build in quieter interludes, sand bodies stack when discharge was flashy and sediment abundant. Buried organic matter in such basins can lock away additional carbon for long intervals, thickening the long-term drawdown begun in mountain soils. Later, if the basins are folded or uplifted, those same packages set the stage for new cycles, sandstones that drain well and host rapid weathering, shales that break into platypines, carbonates that fizz and carve caverns under streams. In this way, the thermostat effect of mountains echoes outward into the plains that fringe them and the shelves that face their rivers. Vegetation teams with stone in this quiet engineering. As uplift lifts land into the clouds, plant communities sort themselves by temperature and moisture. Cloud forests gather on ridges, mosses and lichens cling to boulders. Alpine meadows quilt saddles and benches. Conifer belts give way to crumb holts and then to bare rock and snow. Each belt drives a different style of weathering: leaf litter, acidifying soil solutions, deep roots stabilizing slopes and pumping water to react with minerals, mycorrhizae mining phosphorus and leaving microenvironments of altered pH, canopy interception smoothing the pulse of rainfall. On steep slopes, tree throws and wind throws open soil patches, where meteoric waters access fresh mineral grains. On rock faces, freeze-thaw and biofilms etch micron-scale pathways that later become fractures. Where grazing mammals move with seasons, their trails compact and channel runoff, focusing dissolution in treads that cut into bedrock. Where beavers or their ancient analogues build and abandon dams, porosity and redox swing, altering how fast organics oxidize and how much bicarbonate streams carry away. The living mantle thickening upon mountain shoulders is a reactive membrane, breathing CO2 in the long term toward stone and then toward sea. Mountains also shape dust, which in turn feeds back on ocean biology and continental weathering. Dry valleys and outwash plains become sources of fine particles that ride winds to distant basins and seas. This dust brings iron to pelagic waters where phytoplankton are limited by trace metals, seeding blooms that move carbon downward. On land, dust settles as loess, building thick, soft blankets on leeward slopes and plains. These loess hills store water and host grasslands, which change albedo and transpiration in ways that can alter local climate. They also weather into fertile soils rich in carbonates that perpetuate the carbonate-silicate cycle by dissolving and reprecipitating, with each rainfall. Dust layers in ice cores and lake sediments rise and fall with the strength of winds and the exposure of glacial outwash, marking the breath of cold times when mountains fed more dust and warm times when vegetation pinned it down. In tectonically restless belts, fluids from depth join the weathering story. Hot springs climb fault zones, bringing dissolved CO2 and calcium. In some valleys, tufa terraces grow where these waters dega and precipitate carbonate, a small local reversal of the normal downstream burial route. In metamorphic aureoles and shear zones, CO2 can be released or consumed by reactions that shuffle carbonate and silicate minerals. If uplift exhumes these zones, atmospheric water meets rocks already halfway changed, and the net direction of carbon exchange shifts. Serpentinization of ultramafic rocks, common in ophiolite belts and high-pressure slices, consumes water and liberates hydrogen, supporting microbial communities in cracks and caves and altering pH so strongly that weathering fronts propagate in unique fashions, sometimes precipitating carbonate within the mountain itself. Each of these niche chemistries contributes grains, ions, and dissolved gases to streams and aquifers that pass the signal downstream to larger cycles. The feedback that gives mountains their thermostat power is delayed and braided. Uplift increases relief and rainfall in some places, enhancing weathering. Weathering draws down CO2, cooling climate. Cooling may slow chemical reactions, but can invigorate physical erosion via frost and glaciers. Physical erosion exposes fresh rock surfaces for later chemical attack. And as global temperatures slide, snow lines lower and ice fields expand, amplifying albedo and further coolness. Over long spans, this web tends to balance. A world with more uplift and active weathering drifts cooler. A quieter world with low relief and fewer active margins lets CO2 accumulate from volcanoes and the mantle, drifting warmer. The thermostat has limits and lags, and its set point shifts with continental arrangements, gateways, and the vigor of volcanic outgassing. But its presence is persistent enough that when you trace carbon isotopes through marine limestones and match them to proxies of uplift and erosion, the alignment feels like the slow nod of a large creature at rest. Rivers fed by highlands are the conductors that carry the signal. As they descend, they braid and meander, sort cobbles from sands, make bars that flip in floods, and cut floodplains where soils breathe CO2 back out or bury it as peat. In bedrock reaches, nick points migrate upstream, where base level drops or uplift pulses, and each migrating step rejuvenates the channel, steepening slopes and energizing weathering on hill slopes that respond to the new grade. Landslides triggered by storms or small earthquakes scrape soil and expose bedrock. In their fans, groundwater pathways rewire and springs shift, delivering different chemistries to valley floors. In deltas, the signal diffuses into lobes that build and abandon. But even there, the mineral mix and isotope fingerprints betray which mountain fed which bay. Far offshore, the heaviest particles fall first, lighter clays travel farther, and the finest dissolved lodes ride currents into basins where they contribute to carbonate budgets, shell thickness, and the growth of platforms that later become cliffs and reefs. Carbon laid down by the invisible work of highlands dissolved to ions. When ranges decay, their legacy persists as well. The sediments they shed become the sandstones and shales of future mountains. Their carbonate exports become limestones that can be uplifted and weathered in the next cycle. Their clays drift to ocean floors and, under pressure, release water that lubricates subduction zones and helps fuel arcs, closing the loop between uplift and outgassing. Even their topographic control lingers. Isostatic rebound lifts exhumed cores as outer belts erode, keeping peaks high while flanks lower. River captures rearrange basins long after collision. Rain shadows move as ranges narrow and lower, shifting vegetation and weathering patterns again. Through each rearrangement, the quiet exchange of CO2 for bicarbonate and cations continues, a transaction written into every spring and seeps, every hand sample that fizzes under a drop of acid, every stalagmite band that grew from drip water that had held a little air in its brief journey through soil. Walk a ridge in late afternoon, and the thermostat feels personal. The wind is cooler than the valley. Lichens bead moisture from passing clouds. A thin stream vanishes into gravel and reappears, chilled, a few steps down slope. Crickets change their rhythm as temperature drops. A marmot whistles, and the sound carries farther in the thinner air. None of these small things is carbon. All of them arise because stone is high, and air is cleared of heat a little faster up here. Continue down a spur, and you pass through belts, spruce to fir to pine to oak to grass, each with its own soil, its own rates of decay, its own chemical handshake with the rocks beneath. When you reach the foot, the river carries a faint taste of all those handshakes, a clear, cold brew of bicarbonate and calcium, a promise that a grain weathered on the crest will return as a shell somewhere under a warm sun, and that this exchange, repeated along chains on every continent, keeps the planet's longer breath within the range that forests recognize and that reefs remember, even as the mountains themselves continue to lift, crack, soften, and lean their shoulders into the sky. Imagine the planet's atmosphere as a set of long, slow rivers, and the oceans beneath as conveyor belts with memory. The shape of coastlines and the openings between basins decide where those rivers and belts can flow, so a narrow strait widening by a few dozen kilometers, or a shallow sill deepening by a few 100 meters can reroute winds, tilt rain belts, and teach deserts and monsoons to trade places. When a seaway opens at high latitudes, cold currents can circle a pole unimpeded, isolating a continent and steepening the temperature contrast between ice and ocean. When a tropical isthmus rises to stitch two landmasses together, warm waters that once passed freely are split and redirected, one branch carrying heat and moisture farther into temperate latitudes, another trapped to build stronger trade wind loops. Air answers water with patience. Pressure systems anchor differently. Above new temperature patterns, jets kink and strengthen, storm tracks bend, and the quiet statistics of where rain falls and where it waits to fall shift by degrees that, integrated over millennia, draw new maps of vegetation, soils, and the animals that follow them. At the scale of a globe, the Drake Passage is a hinge with a soft creak. When the gap between South America and Antarctica deepened and widened, currents no longer had to thread a maze of islands and shelves. A circumpolar flow could spin up around Antarctica, a fast, cold river that keeps warm waters at bay and encourages the growth of ice by limiting the delivery of heat to the margin. Ice brightens the planet's mirror, reflecting more sunlight, inviting more ice. Sea level edges down. Deep water formation reorganizes as cold, salty brines sink in new places and at new rates. Nutrients that once pooled in semi-enclosed seas are swept along a loop that fuels plankton blooms where winds mix the surface, drawing carbon into the ocean interior. Winds aloft adjust to the presence of a strong, nearly unbroken current below. The subtropical jet shifts, storm tracks around the southern ocean migrate and tighten, and the southern westerlies, those steady, muscular winds, find a freer path that scours, upwells, and stirs. On distant coasts, upwelling belts breathe more often. Fog visits more mornings. Kelp forests settle their fronds into the cool, nutrient-rich lanes, and small fish learn to school along edges that did not exist before the gate opened. Far to the north and west, the slow closing of a tropical corridor, the rising of an isthmus between the Americas, whispered a different command. Warm, salty water that had once slipped from the Pacific into the Atlantic found itself blocked, and the Atlantic, smaller and saltier, began to host a more vigorous overturning. Surface waters flowed northward, thick with salt from tropical sun and trade wind evaporation, cooled, sank, and returned southward at depth, a pump that transported heat into higher latitudes. Air rode the consequences. Winters softened downwind of the new heat stream, while, on the Pacific side, denied the through-flow, temperatures and salinities adjusted toward a gentler gradient. Rain belts felt the tug on both sides. A strengthened Atlantic overturning helped draw the intertropical convergence zone a little northward on long averages, shifting where monsoons delivered their seasonal deluges. Africa's rain belts wandered, carving lakes into basins that had been dust, then retreating again. The Americas' eastern shores found more moisture in air, arriving over warmer currents. In the chemistry of marine shells, oxygen isotopes recorded new temperature contrasts. In sapropel rhythms and dust stacks downwind of the Sahara, pulses of greening and drying waxed with procession, but hung on the altered background that a closed gate imposed. Elsewhere, the gradual narrowing of the Tethys Sea and the shoaling of its connections rewrote the distribution of heat between hemispheres without needing a fanfare. As fragments of continents drifted and sutured across what had been a broad tropical sea, the exchange of warm surface waters between the Indian and Atlantic sectors became more circuitous. Monsoons built against new walls of land. Summer heating of broad plates drew in moist ocean air more forcefully, the winds climbing mountains newly anchored along the old seaway's margins and wringing storms from them. Rivers intensified on the windward sides, hauling silt and dissolved minerals toward shelves where nutrients would later seed blooms. On the leeward sides, Rain shadows sprawled, and deserts stitched themselves from dune to dune. The Indian Ocean, with its seasonal reversal, strengthened its biannual breath, and coastal upwelling systems responded to monsoon pulsing with rhythms that lodged in fish scales and shell rings. Farther afield, as the Tethys pinched, the pathways of migrating species changed in step. Shallow, warm corridors shrank. Strandings of once connected faunas marked the severing, and endemism took root where currents left eddies of isolation. Small passages carry large leverage. A strait only a few tens of kilometers wide but a few hundred meters deep can decide whether a marginal sea breathes freely or sleeps. If the sill is high, winter storms may not push dense surface waters over it, and oxygen dwindles at depth. If the sill deepens by subsidence or erosion, a new exchange starts, and organic rich muds that once laminated unbroken become mottled as burrowers return. The Mediterranean's alternating history, freshened and isolated when connections narrowed, brined and ventilated when they widened, shows itself in gypsum and salt, then in sapropel stacks paced by monsoon strength, then in healthy bioturbated marls. Each phase begins and ends at gateways where a few meters of depth made the difference between a sea with lungs and a bowl with a film. On a larger stage, the Indonesian throughflow, the sinuous set of channels between Pacific and Indian Oceans, decides how much warm water can slip into the Indian Ocean and up the African coast when sea level drops or tectonics alter the sill depths. The throughflow thins, trade winds rebalance, and rainfall patterns over Australia and Southeast Asia tune to the new song. Coral growth rings, speleothem bands in caves, and dust layers in leeward basins keep these changes as fine stripes that later can be read together as a chorus. Winds are not passengers, they push back. When seaways redirect currents and change sea surface temperatures, they sculpt pressure fields that in turn steer the winds. But those winds then blow harder or softer against the sea, raising or damping waves, tilting thermoclines, and reinforcing or resisting the change. A gateway that reroutes warm water poleward may trigger a tighter, more zonal jet that cages storm tracks. Stormier belts can grind more dust from arid lands and loft it over oceans where iron-starved plankton wait. More plankton means more drawdown of carbon and more export to depth, an ecological lever tied to a geological hinge. Conversely, when a gate closes and a basin warms and stratifies, winds crossing the warmer surface can pick up more moisture, feed heavier rains on land, and increase weathering. The extra riverine nutrients can fertilize shelves, and if mixing is weak, tip them toward hypoxia, tracing a dark letter in mud that spells the name of a strait you cannot see from the core. These loops proceed without spectacle, the planet's quiet preference for feedbacks that take their time. Animals and plants travel by these changes as surely as ships do. A broad seaway through low latitudes acts as a highway for warm water species, and its closure or narrowing isolates provinces that drift apart in character. A high-latitude opening builds a cold corridor and invites cold-adapted fauna to spread around the pole, while discouraging tropical interlopers. On land, winds that reroute with currents carry seeds and insects along new dominant directions. Birds ride more predictable or stronger tailwinds in season, shifting flyways slightly, which over long periods can matter in where gene pools mix. In dusty phases, iron-rich aerosols fertilize downwind soils and point prairies toward greener summers. In clearer phases, the same soils dry and set, favoring woody shrubs. The timing of monsoon onset retunes breeding seasons, and when that timing changes slowly, behaviors stretch. Populations migrate piecemeal, and the fossil record preserves the echo as changes in species range margins and abundance curves rather than as sharp boundaries. The sedimentary record traces gateways with an understated pen. On either side of a fresh opening, grain sizes and mineral assemblages in contourates, the drifts built by deep currents, shift as bottom flows accelerate or change direction. Anisotropy in magnetic fabrics aligns with the new roots, a subvisible compass in clay. Shallow water sand bodies built by tides grow taller and steeper when a strait focuses energy. Their crossbeds thicken and adopt herringbone sets that tell of reversals and spring-neap rhythms. Pebble lags at the base of channels mark phases when the gate pulsed stronger. Offshore, isotopes in the calcareous shells of foraminifera tilt toward fresher or saltier values, depending on whether the new circulation dilutes or concentrates salinity. Neodymium and lead isotopes in fish debris and clays point to changing provenance of waters and dust. Faunal turnovers in microfossils record the first arrivals and last departures across the gate. None of these signatures is a headline. Together they triangulate to a hinge that swung quietly while mountains far away and lavas deep below enrolled it in larger arcs. Some gateways open and close many times, riding sea level changes and tectonic breathing like doors on a spring. During low stands, shallow connections fall dry, severing marine migrations and building land bridges where mammals and herpetofauna cross. During high stands, those bridges drown and corals colonize the new passes, knitting reefs that in turn influence flow by baffling currents and raising sills. In tropical archipelagos, reefs that lock into chains can filter waves and create lagoons where warm, clear waters incubate larvae. If a pass erodes or subsides, the filtering weakens, waves bite into the reef edges, and sediment budgets reshuffle from carbonate sand to rubble, with food webs adjusting accordingly. Over multiple cycles, the stratigraphy stacks packages that each begin with a transgression, marine sands over soil, build to a maximum flooding where fine carbonate muds and deep fauna settle, and then shallow again to beach and dune. Nestled within are the tidally forced rhythmites that whisper of the width and depth of the conduit at that time. Even the sky's high currents acknowledge the doors below. Jet streams trace thermal gradients. When a gateway like the one around Antarctica sharpens a circumferential temperature line, the jet tightens and zips. When a warm current is redirected to brush a continent's coast, a thermal ridge grows overhead and the jet kinks around it, focusing storm genesis just offshore and altering rainfall hundreds of kilometers inland. In cave speleothems, oxygen isotopes swing as moisture sources shift from one ocean to another. In Lake Varbs, coarse summer layers thicken or thin with monsoon vigor. In Laos, dust grain sizes coarsen when winds strengthen under a new pressure pattern, and thin when soils hold under softer flow. These archives are local and quiet, but synchronized across regions, they reveal the wide reach of a gate opening a notch wider or swinging a notch closer. Because these changes are gradual, ecosystems often evolve alongside them, learning the new wind and water over tens to hundreds of thousands of years. Mangroves creep along coasts where currents now deliver warm water in winter. Kelp forests shift poleward with cooler tongues. Upwelling fishery species toggle dominance as the seasonal timing of wind pulses drifts by a week, then two, then a month. Inland, rain belts lingering longer over one basin carve deeper networks there and starve another. Soils on the favored side thicken, hold more water, and foster closed canopy forests, while the other side leans toward open savanna and evaporites. Archaeological horizons later inherit these settings. Camps concentrate at the mouths of upwelling fed estuaries. Middens thicken where shellfish prospered. Rock art clusters along rivers that ran perennially in intervals when the gate-fed monsoon was stronger, then thins when it slackened, and water retreated into springs and seeps tucked against shaded cliffs. Stand on a headland where two currents meet, and you can feel, even in a single day, a miniature of the long story. Fog in the morning, as cold water wells up. Sun by noon as the wind eases, a line on the surface where slick and ripples interleave. Seabirds quartering the seam where plankton concentrates. Far below, the boundary current combs the slope and builds a drift of fine sand that will one day be stone. Farther out, eddies peel away and carry larvae across invisible borders. The cliff under your feet is made of old beach or shelf sands laid down when a previous arrangement of gates drew waves and winds into this angle. The plants at your ankles are salt-pruned and wiry because of the wind that today's gates guide along this shore. It is all smaller than a supercontinent and subtler than a flood basalt, and yet the cumulative shuffling of sky rivers and seabelts by the opening and closing of passages writes whole chapters in where deserts breathe and forests condense, where rains arrive and how they leave, and how the planet teaches its air to move along the edges that rock leaves for it, pausing and pressing and then gliding again. Imagine land before shade, low mats of algae and lichens hugging damp rock, dark crusts stitching thin soils in quiet polygons, the wind lifting dust from bare flats, and the first streams wandering shallow and wide across bars that shifted with every flood. Into this bright openness, small plants begin to lean upright, stems thickened by tiny tubes that carry water and nutrients, leaves unfurling thin as a breath to meet the light, and most importantly, roots taking hold. A root is more than an anchor. It is an instrument that plays the ground. It slips between grains, pries at cracks, releases acids and chelators that pull metals from minerals, trades sugars for phosphorus and nitrogen, with fungi that lace through the soil like fine white smoke. Together, plant and fungus turn rock to soil, a grain at a time, knitting loose sediment with threads of life until the surface can hold water longer after rain and resist the tug of a rising stream. Where roots grow dense, bank faces stand a little taller, floodwaters bite a little less, and the river, which once split into many shallow threads, braided around bars of loose grit, begins to prefer a single sinuous path. Meanders bloom, point bars grow like crescents of sand and silt, cut banks polish and undercut. Oxbows are pinched and left behind as quiet, curved lakes for dragonflies and slow fish. In the rock record, this change writes itself as a switch from piles of cross-bedded gravels to packages of fine overbank muds, levees, crevasse splays, and paleosols, the red and brown horizons of ancient soils, with root traces like soft wires preserved as ghostly tubes. As leaves broaden and canopies thicken, the sky near the ground cools by a degree, then another, in the dappled shade. Evapotranspiration, the gentle lift of water from soil through stems to air, feeds clouds and recycles rain over land, so that storms that once hurried inland and thinned now linger and swell. The smell of geosmin after a shower grows more common. The pulse of small streams steadies as roots sponge up floods and leak water back during clear spells. On slopes, litter falls, decays, and darkens into humus. Soil profiles deepen into horizons that sort by color and chemistry. Iron reddens in well-drained tops, carbonate gathers in drier layers below. Clay minerals line pores. Carbonate nodules bloom like buttons in arid belts. Concretions shape around roots where carbonates precipitate from waters that plants pulled upward by day and let recede at night. Each soil is a slow memory, recording the balance of rain and dryness, the kind of plants that lived above, the time between floods, and the chemistry of the rock beneath. Buried by later floods or dunes, they become the quiet pages in which future readers find the delicate casts of rootlets and the flecks of charcoal from fires that passed softly through understory and grass. The partnership that makes all this possible happened mostly out of sight. Fungi press into root cells, exchanging fine branches of themselves, arbuscules, for carbon handed to them by the plant, while ferrying phosphorus and micronutrients from beyond the root's short reach. Cyanobacteria and other microbes fix nitrogen in the shelter of soils newly rich in organic matter. Lichens and cryptogamic crusts colonize bare rock and sand first, laying films that catch dust and seeds, then retreat to edges as taller plants arrive. The chemistry these communities write into the ground changes rivers and the sea at once. Silicate minerals weather faster, flooding streams with bicarbonate and cations that drift to the ocean to build carbonates. Phosphorus released from apatite and held in soil by iron oxides and organic complexes now travels in pulses during floods, fertilizing deltas and shelves. Dissolved silica delivered from rock feeds diatoms in coastal waters, iron in tiny amounts. Blown as dust or flowing in rivers, nudges plankton into blooms. With more nutrients, more organic carbon sinks, and oxygen in surface waters often rises, while at depth the delicate balance shifts with mixing and season. Over long reaches of time, the net effect is a drawdown of atmospheric carbon dioxide as weathering sips from the sky and burial tucks carbon away in coals and organic-rich muds, while oxygen rises as plant and algal photosynthesis outpaces oxidation. In the strata, carbon isotopes tilt heavier during these burial phases, while charcoal counts climb as oxygen crosses thresholds that allow frequent, low flames to move through leaf litter without consuming the canopy. Rivers learn to write longer sentences under the new banks. Meanders migrate laterally, painting floodplains with ribbons of sand and silt that show their curvature in plan view maps of ancient systems. Crevasse splays spill fans of coarser sediment into back swamps when levees fail under strain, and then the breach heals, smoothed by roots and reeds. Oxbow lakes fill with fine laminations, their valves marking years like rings until a new avulsion cuts the main channel to a different course. In the cross-sections of these floodplains, paleosols stack and mature. Glide colors tell where groundwater lingered. Slickened sides mark swelling clays that shrank in drought, and nodules of carbonate or iron cluster where redox danced with seasons. Bank strength lets channels incise deeper between floods, and terraces step along valley sides where climate pulses lifted or lowered base level. The rhythm of cut and fill tunes to precipitation pulled by plants and returned to air as mist and cloud. Downstream, deltas become more cohesive, lobes build farther seaward before failing, and the coastline begins to grow its own lacework of distributaries, bays, and marshes where wetlands filter water and store carbon as peat. Plants themselves grow taller and stranger as wood evolves to bear height. Lignin stiffens stems. Secondary growth thickens trunks. Rings appear where seasons pace cambium. Leaves design themselves in countless arrays to balance water loss with light capture. Broad, pinnate, needle-like, lobed. Forests arrive in patches, then belts. Lycopsid swamps with towering club moss trees and roots that radiate as stigmaria through saturated muds. Horsetail stands feathering pond margins. Seed ferns and early conifers exploring drier slopes. Later, true seed plants building mixed canopies and the first recognizable woodlands on hills far inland from seas. Under them, in the darkness where midday is twilight, leaf litter combs rain into drops that arrive gentler on the soil, and the forest floor grows architectures of decay. Fungi building cords that ferry nutrients, isopods and millipedes nibbling at edges, mites and springtails hopping like sparks, beetle larvae tunneling, worms weaving. These small residents are the other half of the greening, forming the soil food web that turns fallen carbon into humus and back again, and their burrowing changes infiltration, aeration, and root paths in ways that feed back to the stability of banks and hills. Between trees, early terrestrial animals find corridors of shade and moisture. Arthropods, already abundant in leaf litter and on bark, diversify into forms that graze, hunt, and scavenge under the damp canopy. Their molts and mandibles etch patterns into the lenses of shale that capture a fallen leaf and the tracks that crossed it before burial. Later, vertebrates that nuzzled rivers' edges learn to breathe air with lungs more reliably and push into fern-choked backwaters where roots lace the mud, leaving sinusoidal trackways and belly drags in fine silt that hardened before the next inch of flood carried another film of clay. The greening creates shelter as much as it creates food, shade to hide in, humidity to keep gills wet while bodies learn to seal, and a ladder of roots and fallen trunks that breaks the long slope from water to upland into steppes. Fires also become part of the mosaic once oxygen is high enough. Low burns, clear underbrush, and open seedbeds. Some plants learn to sprout when heated, or to drop seeds that need smoke. Charcoal gleams in thin laminae as proof that flame passed without turning the world to ash. On hillsides, the texture of weathering deepens because roots reach farther, water lingers longer, and microbial films etch faster. Feldspars turn to kaolinite in humid heat or to smectite where seasons swing. Micas lose sheen and free potassium. Iron becomes hematite or goethite, depending on how freely water moved. Manganese paints nodules in horizons where redox fronts sat during wet-dry cycles. Calcareous soils in drier belts precipitate hardpan layers, calcretes that record long pauses in sedimentation and limited leaching. In wetter belts, glaze form where groundwater smothered oxygen. In cold belts, cryotubation thrashes profiles into mottled pillows. In volcanic belts, ash weathers to allophane and immigolite, spongy clays that hold water and phosphate in unusual ways. Each profile is a palette and a diary, and when buried beneath floodplain sands, they become paleosols whose clays tell mineralogists about rainfall and temperature long gone, whose root casts record vegetation density, whose carbonate nodules preserve carbon isotopes from CO2 breathed by roots and microbes in that ground. The decline in dust that follows greening is another quiet turn. Roots fix topsoil that wind once lifted easily. Canopies calm near-surface air and break gusts into eddies that do more mixing than lifting. Surface crusts built by fungi and exudates bind grains. Far downwind, lowest blankets thin and the grain sizes fine, telling of weakened winds and stronger cohesion at source. Over the sea, iron delivery by dust slackens in some corridors and strengthens seasonally in others where vegetation opens during cold or dry phases. These adjustments ripple into ocean biology and back into rain. Plankton blooms pulse differently, drawing down carbon and releasing dimethyl sulfide that seeds clouds more or less depending on who is blooming. Clouds cast shade and adjust surface temperatures that steer winds slightly. Winds return to the plants, with those small differences integrated into a climate that plants themselves helped create. Over very long arcs, the establishment of forests enhances the silicate weathering feedback, which leans climate toward cooler states, while oxygen high enough to support fires keeps ecosystems patchy, renewing soils and recycling nutrients without allowing uninterrupted mats to rule for too long. In the fossil record, the greening shows up as more than leaves pressed into stone. Rhizoliths, tubes of carbonate and iron where roots once lay, trace networks through soils, spores and pollen assemble in cores and shales to show the dance of plant groups as climates shift or as gates reconfigure currents that carry moisture. Coal seams stack in wet basins, smudged with plant fragments so well preserved that cellular details still shine in thin section. Tree stumps stand in place in some horizons, their roots still in the soil that fed them, their trunks truncated by a flood that later laid sand where canopy once stood. Clay mineral assemblages shift towards those formed by intense leaching or seasonal dryness, indicating new balances of water and temperature tied to forests. Boron in marine carbonates hints at pH moving with CO2. Strontium ratios drift with the balance of weathering between old crust and young lavas, but the sheer volume of weathering rises as slopes are covered by green. Even river architectures in ancient sandstones betray the change. Single-thread, lateral accretion structures with gentle stratification replace the thick, steep crossbeds of wandering, bar-braided rivers, telling of banks that held because roots held them. The net outcome of all these slow adjustments is not uniform across the world. In some regions, greening clings to floodplains and deltas, while uplands remain open under strong rain shadows. In others, montane cloud forests knit ridges while valleys lie in sun. In still others, wetlands stitch across broad, flat interiors where rivers meander lazily and peat accumulates for millennia. Each pattern changes the way storms translate into discharge, the way carbon moves from air to root to soil to stream, and the way nutrients pause or rush through. Where forests pull more water into the air and return it as rain, monsoon belts can sharpen, and the hum of season becomes stronger across entire continents. Where deep-rooted woodlands keep soils porous in dry seasons, streams flow as clear threads rather than bursts of mud, and fish evolve to live with constancy rather than drought. Animals that browse leaves and those that graze grasses divide the open and the shaded between them. Predators learn to ambush at edges where light becomes shade. Pollinators draw lines from flower to flower that later become migration paths across mountain flanks and valleys. Stand in a riparian grove on a summer afternoon and the difference is ordinary and complete. The air under the leaves holds a little more moisture and fewer degrees of heat. Gnats drift in bars of light. The river runs clearer than it would have under bare banks, its edges carved into soft shelves where roots braid through sand. The silt at your feet is laminated with thin floods that rose and fell without tearing the place apart. Birds scold and then settle. A dragonfly hangs in a patch of sun, and the patch trembles with the water's reflection. The unseen mega-event here is the invention of shade and soil depth, of roots that stitch and hold, of rivers learning to curve under gentle hands. It is the long, small act by which plants tipped the planet's balances, carbon, water, sediment, toward new equilibriums, and then held them there by growing rotting, breathing, and burning in soft cycles that turned rock into ground you can walk on barefoot, into banks that lean and then stand, into a canopy that mutes the day just enough that you can hear the rivers even talk as if it were telling you how the change happened. One leaf, one grain, one rain at a time. Imagine a world where shade thins and horizons lengthen, where the breeze moves more easily because leaves are narrow and the ground is trimmed close to the light. Grasses do not look like a revolution, but they rewire daylight into sugar by a different route, C4 photosynthesis, that sips water more carefully and keeps working when air is hot and dry. In quiet steps during the late Miocene and into the Pliocene, these grasses spread across belts on several continents, taking root where seasons sharpened, where monsoons pulsed, where soils were deepening into dark loams rich with fine roots. Their blades carried tiny bodies of glass, phytoliths that made mouths work harder. Their growth came from the base, so a bite did not kill the plant, but invited it to grow again. Their seeds rode wind and stomachs. Their stems burned clean and quickly, and after fire, they were the first to green. Under that new regime, landscapes opened into savannas and steppes, mosaics of short trees and long sightlines, and the animals that lived there redesigned speed, teeth, and habits to meet the ordinary, endless distance. Teeth became the main ledger of this change. Browsers with low-crowned molars, built for leaves, gave way in many places to grazers with hypsodonty, high-crowned teeth that erupt slowly like stone escalators, ready to handle the mixed abrasion of silica-rich blades and grit lifted by wind. Enamel grew thicker, cement-filled valleys, microwear shifted from soft scratches to denser pits and cross-hatching. In the chemistry, carbon isotopes in enamel tilted toward values that speak of C4 diets, and those signatures stacked through time in drawers of teeth from horses, antelopes, rhinoceroses, and many smaller lineages, each drawer a quiet map of grass gaining ground. Jaws strengthened to manage longer chewing. Skulls broadened for masseter muscles. The muzzle lengthened or narrowed, depending on how precisely lips needed to choose. Herbivore bodies lengthened in limb and shortened in toe count. Elastic tendons and springy ligaments stored energy. Spines stiffened for efficient gallops, shoulders freed to swing. Herds grew as a way to manage space and eyes. Migration became not a gamble, but a plan, timed to rain and the flush of new blades that follow fire, or the first storm of a season. Fire, wind, and hooves collaborated in these open rooms. Fine fuels carried low, fast burns that favored grasses over shrubs. Many seeds learned to wait for heat or smoke. Bark thickened on trees that persisted, and crowns resprouted from protected buds. Termites rose as quiet engineers, building mounds that lifted soils and vented gas, patching the ground with islands of fertility where grass stood greener. Dung beetles rolled and buried nutrient packets. Grazers trimmed lawns short enough that new leaves grew tender and rich, luring teeth back and anchoring a feedback that kept woody plants at bay. In wet years, shrubs and trees advanced. In dry years, fire pushed them back. Roots in their billions stitched soil, built black horizons that held moisture through weeks without rain, and made the surface less likely to slide when storms arrived together. Aeolian dust still moved, but the belts that once sent it endlessly across basins were interrupted by cover, and what dust remained fed oceans downwind, where tiny blooms rose and fell with seasons that grass had helped sharpen. Predators lengthened limbs in answer. Cats learned to sprint and faint. Dogs and their kin learned to run farther and flush. Talons on open country raptors lengthened and wings broadened for low flight over heat-shimmering fields. Snakes patterned their scales to vanish among stems. Small mammals tunneled and sprang with equal practice. Vision favored horizon and twitch. Ears widened and rotated. Nostrils took the wind's temperature and information. The drama was daily and patient. A stalk that could last hours. A chase measured in sprints. A collapse into shade when the sun pressed too insistently. Bone beds in old waterholes kept the record of these lives, the attritional loss of the unwary and the old, while trackways across damp flats froze brief scenes into stone. A herd flowing around a patch of soft ground, a lone walker cutting diagonally to join, a predator's pace changing as it shifted from trail to approach. In spores and charcoal, the rhythm of burn and regrowth settled into a long hum, its volume rising and falling with the breath of wet and dry years that moved like tides across continents. The soils under grass wrote their own steady chapters, deep dark horizons, rich in organic matter. Mollisols, built where roots penetrated and died in place, a lacework constantly renewed. Carbon made its long residence there and then, grain by grain, moved downstream as bicarbonate and tiny fragments joining the sea's carbonate factory in pulses linked to seasons, storms, and grazing pressure. Carbonate nodules formed in drier belts where evaporation exceeded rainfall. Their concentric rings kept CO2 from roots food and microbe as isotopic diaries, each nodule a slow bead on a string of years that carried past dryness into the present. Microaggregates held by fungal glues and root exudates gave soil the fine crumb that resists crusting, so rain infiltrated rather than striking and running. That infiltration smoothed floods and fed springs through dry spells, changing the hydrograph of rivers that once surged and slept into rivers that murmured more steadily. In the stratigraphy, channel sands with lateral accretion surfaces sat beside overbank silts with root traces, Aeolian sheets with low-angle crossbeds tucked against river packages. Paleosols stacked between crevasse splays told how often water stayed out and how often it returned. The air took on a slightly different composition where grass ruled. C4 photosynthesis opens fewer stomata to fix the same carbon when air is hot and bright, so fields exhaled less water for the sugar they made and could push midday humidity a little lower above their own surfaces. Nights cooled more quickly under open skies, while days warmed and stirred air close to the ground in small eddies that made scent travel and sound carry. Over regions This balance fed back on clouds, moisture recycled differently than over forests. Thunderheads grew later in the day, and in different places along the gentle rises of plains. Monsoons arrived with the same calendar, but with edges shifted. Tens of kilometers, then hundreds, over centuries. Loess deposits downwind of dry season belts, thickened and then thinned as vegetation waxed and waned, their grain size coarsening when winds strengthened, fining when cover held. Within those stacks, snail shells and root casts traced wetter interludes. Magnetic grains weathered from basaltic dust adjusted to rainfall. A quiet barometer for the line between grass and shrub moved back and forth. Birdsong changed with open space. Larks and pipits began to speak in arcs that rose against the sky, displaying over territories written in scent and step. Bustards and grouse learned dances weighted with air. Cranes stitched wetlands with calls that carry. Quails wrote punctuation into edges where grass ran to shrub. In the fossil record, the birds themselves are light, but their presence lingers in gizzard stones, in pellets from raptors that later calcified in caves, in trackways pressed into wet margins of pans that dried in high sun. The three-toed signatures of a visitor that left no other bones in that place. Insects scaled to the lawn as well. Orthopterans chirped in textures matched to a height. Ants moved soil in volumes that approached rivers' work on small scales. Butterflies timed migrations to green waves that ran poleward or upslope with spring. Bees learned the mosaic of forbs and grasses that bloom after fire and seeded the next flush. Along edges where patches of woodland remained, browsers and mixed feeders worked margins while grazers trimmed centers, and that tension held the pattern in slow, dynamic balance. Clearings in trees filled with grass. Thickets advanced into open if fire slept too long. River corridors kept ribbons of shade that cooled water and allowed fish that preferred it. Elephants and their kin, where they lived, broke branches and spread seeds, pushing against woody encroachment in one era, inviting it in another when ranges shifted. Termites and earthworms moved nutrients vertically, bringing subsoil nearer the light and drawing leaf fragments downward. Nitrogen fixers set small bonfires of fertility across plains. Dung scattered by herds incubated specialist floras and faunas whose life cycles turned on brief rains and the passing of hooves. In long droughts, lawns browned, but crowns slept, roots hoarded. When rain returned, the first flush arrived with a green so sudden it seemed to rise from the memory of blades themselves, drawing migratory lines back to valleys and fans that had held water longest. In enamel and bone, the record of this world is consistent across basins. Delta 13C values in teeth rise towards C4 signatures with time in many regions. Oxygen isotopes track water stress and seasonality. Strontium tracks movement across bedrock provinces as herds walk their ranges and drink from different basins. Wear patterns record the season at death and the mix of grass and grit. Microfaunal assemblages, rodents, lagomorphs, small antelopes shift towards species that favor open, patchy cover. Owl pellets gathered in caves show the same turnover. Coprolites from grazers carry silica bodies that name the grasses consumed. Even the dust caught in enamel pores and sinuses records local wind regimes in trace minerals and grain shapes. Layer by layer, the stack of small data matches the large picture, painted by channel sands and paleosols, by charcoal counts and fire scar rhythms on ancient wood where it survives, by the geographic spread of taxa adapted to run, graze, and watch the horizon. For primates living near the edges of these fields, the new openness altered ordinary decisions. Standing to scan became useful where sight lines stretched. Moving between patches favored more efficient strides. Midday heat favored shade sharing and rest. Dawn and dusk favored travel. Hands that could carry water or food across bare ground gained small advantages multiplied over seasons. Diets broadened to include more grasses and the animals that ate them. Tools shaped from stone at damp margins and brought into open patches pushed teeth a little less and edge a little more. Fire, once gathered from lightning, later tended and moved, made sleeping on the ground safer when light could be kept at the edge of dark. None of this needed drama. The open country simply asked different questions than the forest had, and bodies and habits that could answer those questions steadily persisted. In sediments near old lake shores and springs, footprints pressed into wet ash cross in pairs and groups, stride lengths matching adult and juvenile pace. Direction vectors showing a preference for water and for the easiest slope, the sort of quiet scene that repeats in every generation without seeking a headline. The grassland pulse did not occupy all latitudes or all longitudes at once. It moved like a slow green tide, advancing on some continents while retreating on others, depending on how gateways guided currents, how mountains pulled rain from air, how CO2 and the temperature together favored C3 or C4 leaves. In South America, high plains stitched themselves to Andean shadows. In Africa, savannas spread under belts of summer rain and retreated when rain belts drifted. In North America, tall grass ceded to mixed and short grass steppe, where seasonality and rain shadows strengthened. In Eurasia, steppe flowed east and west along a long corridor under westerlies. Each region housed its own experiments in speed and teeth, in burrow and mound, in song and flight. The fossil record honors the differences while tracing the shared grammar. A rise in hypsodonty indices, a shift in phytolith assemblages of soils from forest to grass types, an increase in fire proxies, a remodeling of river architecture toward cohesive banks and sinuous channels, a turn in dust flux recorded in leeward basins and marine cores. Stand in a prairie at dusk and you can feel the logic. The day's heat lifts away like a light blanket. The wind slows and talks in a smaller voice through stems. Scents carry farther. The ground holds a day's worth of sun in a thin layer that cools under your palms if you rest them there. A nighthawk folds and dives. Far off, a herd turns as one, not hurried, only aligning for the next patch where blades are new. A fox prints 4 small ovals in damp dust and pauses to listen. Somewhere behind you, A line of ants makes an evening errand between mound and a plant that leaks sweet at the cut stalk. The unseen mega-event is not a single invention, but a suite, a pathway for carbon that wastes less water, a tooth that grows taller, a fire that stays low and returns nutrients without scarring, a root that remakes soil into sponge, a horizon that teaches eyes to watch differently. It is grass practicing patience until whole regions choose its way of being, and the record of that choice lying quietly in teeth, in little glasses, in soil, in soot, in the curve of old rivers, in the long bones of animals that learned to move as if distance were ordinary and time plentiful. Imagine a landscape that edits itself in seasons and in centuries, a long chain of basins stitched along a faulted seam where the continent is very gently trying to part. The ground steps down in tilted blocks, each with a catchment to collect rain and a sill to spill it. Lakes appear and fade with the patience of breath. Shorelines creep upslope when summers linger and pull back to reveal salt and fish bones when winds take the rain elsewhere. Along these rift valleys, volcanoes dust the water with ash that settles in thin, dartable lines, and hot springs add minerals that paint terraces and sweeten seeps where animals gather. The air above such valleys is unruly in small ways. Lake breezes that reverse by afternoon, storm cells that rise on heated flats and spill in sudden veils, morning mists that hide the distance and cool the skin. A day here has edges you can read with your body. A century has edges you can read in the stack of silts and sands along a cut bank. 100 centuries stack into a book that shows how water wrote the routes between shade and open, high and low, wet and dry, and how bodies learned the grammar by walking it. In these settings, rivers and lakes become calendars as much as pantries. When rift shoulders rise a little under silent tectonic lift, rain falls a little more on one side, and new springs appear along the foot where faults ease water upward. When the monsoon belt shifts by a degree of latitude, the big lakes freshen and expand. Fish nurseries bloom in reed beds, and shorelines swing outward to cover old camps in meters of silt. When the belt retreats, the same lakes draw down to linked basins and then to bright pans, leaving stranded beaches with lines of shells where children later play. Each pulse of water redraws the roots of ungulates, and where hooves go, hunters go. Each retreat clears a corridor between basins, and where corridors open, foragers carry edges, fire, and stories into flats that last just long enough to leave a layer of chips and bone tucked into the lee of a basalt boulder. In the sections that erosion cuts for us, these alternations look like pages of light and dark, windblown sand whispering of drought, then laminated lake mud counting years, then a sheet of ash thin as a palm leaf, then again a flood splay that dropped pebbles and a single cracked hand axe as the channel shifted by a body's length and forgot that bank. Shorelines are teachers. They offer grass in a green rim in the early morning when dew collects. They offer shellfish and snails where water is low and warm. They offer a mirror that draws herds at dusk and predators at their flanks. They offer pathfinding because a lake's curve draws you around obstacles without committing you to steep climbs. When the lake lifts and saturates the plain, people take to the shoulders and use the wind to read the line between open water and reeds. When it falls, the same people cross the floor where fish bones strew and springs still run, windows of wet in a dry bowl. Over lifetimes, a person can learn 3 or 4 faces of a single basin. Over generations, the shapes shift enough that stories must keep the memory of old inlets and dangerous muds. In the rock, toes pressed into wet ash reveal a stride that shortened to test the soft ground and then lengthened on firmer sand. In the silt, cut-marked bones pause where a carcass was opened at the water's edge and finished under shade. In a cave above the shore, a fan of charcoal and a scatter of flakes record an evening of warmth and work, while wind made the lake shiver under moon. Rainfall patterns nudge everything without needing to raise their voice. A slightly stronger monsoon means rivers cohere into longer threads that keep their banks under roots, and floodplains hold water in oxbows into the late dry season. A slightly weaker one means braided channels wander and leave glare-white bars that glare back heat, and travel favors dawn and dusk to spare feet and eyes. A cooler decade lifts the thermocline in stratified lakes and brings nutrients to the surface more often, feeding fish runs that concentrate in inlets. A warmer one stratifies longer and fish cluster in spring-fed coves where cool water lays like a sheet over the shelf. In such a world, toolkits flex with water, flakes and scrapers near carcasses on open ground, heavier cores and hammerstones near cobble bars, light retouched pieces cached in upland alcoves for the season when the valley floor floods and the only way through is along the basalt steps where hard stone is scarce. In middens tucked behind boulders, seeds with heat-blistered coats whisper of parching and pounding. Bone-grease pots in shallow basins near hearth circles speak of a culture that learned to take calories gently from what remained after meat was gone. Ash enriched with phytoliths from sedges and reeds shows time spent weaving and lining sleeping spots where damp would otherwise creep up from the ground. Fault scarps are both obstacles and gifts. They lift springs along their toes, banding the valley with green steps where shade and water linger. They block a direct line and force paths through passes that become crossing points for animals and people alike. They dislodge blocks that become lookouts with breezes and visibility that keep biting insects away and bring scent earlier to a watching nose. The basalt that caps some scarps breaks into predictable shapes when hammered, flakes with long cutting edges, cores that can be carried for days and still hold promise. And so the geometry of rock becomes a quiet partner in diet and safety. In the record left, certain raw materials reappear in sites many kilometers from their source, a signature of recurrent movement along the same corridors as water rose and fell, and as vegetated belts marched up and down the slopes with the line of cloud. Strontium in enamel from teeth taken in different parts of the same valley shows childhoods spent in different drainages. Before adulthood brought families together at the lake when it was high, then back to separate hills when it was low. Oxygen isotopes in the same teeth track the season of weaning and the lean months when more C4 plants or their grazers made up the diet. Wind across open water makes its own weather that matters at human scales. Afternoon breezes cool the shore. Mornings hold still air that lets smoke rise vertically from a small fire and not betray its presence. Storms stack waves that eat at points and leave sand in embayments, and behind those points are pockets of flint or chert tumble just enough to take a good blow. The great gates of climate, the seaways opening and closing far away, are reduced in such valleys to the arrival of a stronger lake breeze season and a fringe of fog that keeps mornings damp a few weeks longer, enough to change when reeds can be cut and when tubers are easiest to pull, enough to shift the best days to travel between basins. And underfoot, the muds and sands remember more than we would guess. Varved clays that count seasons, thin charcoal sheets where a grass fire ran and spared the shrubs that now clutch the slope, subtle magnetic shifts in a mud lens that tell of the lake's chemistry breathing with wind and rain. These are the measurements behind the softness of a root, the reason one bench stays green when another burns, the justification for opening a cache of flakes at one spring and not another. On longer beats, the rift itself is a hinge for movement. Lakes that once were separate touch and spill over a low divide, and a new corridor opens that will not last a century. A sill subsides and a waterfall becomes a rapid, then a riffle, then a memory, and fish go through where once they were trapped, and people follow with webs and baskets and obsidian carried from a far promontory. Ash falls, a veil of pale dust from a volcano beyond the horizon. Soften the sound of footsteps for a day, and then, when wetted and set, preserve the day as footprints and drips frozen in mid-fall. The ash also sets clocks that reach across basins so that a hearth's charcoal on one shoreline can be found to have glowed on the same week as a butchered hippo on another, and a string of prints between them. In dry phases, caves that were damp become good storage for wood and for fruit dried on racks near the mouth. In wet phases, the same caves drip steadily and grow skins of calcite that seal and keep for later a few of the fibers and seeds dropped careless under the sleeping shelf. Coasts elsewhere in the world migrate with sea level, and those migrations send their echo far inland by bending storm tracks and the reach of monsoon arms. A higher sea floods low deltas and throws more moisture into air currents that track up rift axes. A lower one deepens pressure, contrasts over warm basins, and may hitch the rains to a different calendar by a few weeks. Those few weeks matter for a species that plans with memory measured in seasons, a birth timed to falling rains rather than rising ones, a larder stocked for a late flush of grasshoppers, a journey started 2 nights earlier to reach a pass before snow crusts break. The timing leaves marks in the chemistry of teeth and in the layers of cave floors. It leaves marks in which animals dominate bones in certain horizons, more fish in seasons of high stands, more small antelope in years when reeds fell back and open flats dominated. It leaves marks in soot trapped in calculus on teeth, a tracer of smoke breathed more in one phase than in another, as evenings grew cool sooner and hearths were tended longer. The quiet mega-events are thresholds crossed without ceremony, oxygen high enough to let fires run gently in savannas, CO2 low enough to favor C4 grass where once C3 shrubs ruled, a sill deepened enough that a lake can overturn in winter and stay oxygenated for fish through a long dry season. A monsoon pulled far enough north that a chain of springs stays connected across the floor of a valley for 3 extra months. Each threshold, once crossed, tilts choices, an evening walk rather than a risky night, a reliance on fish that fatten right before a windy season when nets are most useful, a camp placed 20 meters higher to avoid a flood that now arrives more often because storm tracks bend differently. In the sediments, these thresholds do not announce themselves, but the pattern of human traces shifts in chorus, fewer small hearths and more large ones where groups gathered, more grinding stones where seeds were a larger share, more cut-marked fish spines in layers that align with wind-borne sand sheets, more pigments ground and stored when caves were used longer through cool seasons. Behavior arrives as an overlay rather than a body, and yet the overlay is thick enough to read a way of life tuned to water's patience. Elsewhere on the continent, faulting and uplift draw rain shadows and feed glaciers that pulse dust into the air. The dust lands faintly on lakes as a whisper of iron or a change in grain that inches productivity and guides who thrives. In years when dust feeds a lake just enough, algae grow in tight bands along the shallows and draw water birds in numbers that change the noise and waste on shore. In years without the dust, the band is thinner, and the birds choose another basin, and predators adjust trails accordingly. Walkways along the shore harden under this traffic and are preserved as compacted streaks in silt layers that otherwise would blow away. And those streaks lead archaeologists today to the same easy lines that hooves and feet favored then. Under an overhang where spring water stains the rock, a platform of cobbles grows from years of people sitting, a human-made surface as honest as a termite mound. And in the gaps between stones, a cache of flakes marks a small insurance policy left for another season or another cousin. When rain belts retreat for longer runs, paths turn to rock. Rift shoulders hold their green only in swales and at seeps. Enamel thickens on the teeth of small antelope that now eat more C4 than they once did. Human ankles and hips carry a little farther each dawn to make water and shade connect. Fingers remember quickly the dusting of salt left on skins by dried pans where wild ungulates lick at dawn. Tongues remember the chalky taste of tubers that hold just enough water to wet the mouth for an hour. None of this reads as hardship in the prose of stone. It reads as a phase when the easiest sites to find are a little higher, hearths more often beside seeps, fish bones fewer, and tortoise shells thicker. Then rains swell again, and trackways reappear on ash near the shore in sets that show families walking not hurriedly, but inclining toward the place where pelicans circled, and new charcoals darkened cave floors in bands aligned with speleothem. Growth rings that widened when dripping sped up. Across all of this, the stage is set not by a single invention, but by a combination of moving frames. The rift offers basins and steps, volcanism gives clocks and edges, monsoons drift and return, lakes turn over or hold still, grasses and shrubs trade acres, animals redraw their loops in response, people fold their own loops into those, with fire as a small local climate and stone as a small local memory. The pieces interlock softly, a raised threshold for lake mixing, a lowered threshold for grass advantage, a new sill for fish passage, a modest increase in dust when an upwind glacier retreats, a slight decrease in winter wind that lets smoke rise quietly through an evening and not blow sparks into reeds, a 10-meter change in shoreline that uncovers a shelf of old cobbles just when a family needs to resharpen edges at a place with a wide view. And because the record keeps the small things faithfully, ash laminae, fish spines with cuts, seeds with blisters from parching, flakes refitted to cores found kilometers apart, soot in calculus, strontium tying a child to one valley and an adult tooth to another, the large, unseen choreography becomes legible as a pattern of gentle constraints and opened doors, the kind of scene one can walk through in imagination at a pace that matches the lake's slow lift and fall, with the understanding that the same steps will fit again tomorrow, even if the waterline has crept by the width of a hand. Let's let the night take it from here. I'll leave the screen low and the world quiet. When morning finds you, share where you're watching from and which hidden era you want to drift through next. If this helped you unwind, a soft tap on like and subscribe keeps these sleepy journeys alive. Rest easy.